ONX-580. Is there anything specific that you need to make sure I cover as I go through this besides the copper DSL? Is there anything copper that somebody says, hey, I am struggling with this, I need help with this? Anything there that I need to know about that I make sure?
You're asking just about copper or the
Copper,
totality of everything we're going over?
copper, DSL, whatever you need me to go over. I want to make sure I don't miss anything.
Oh, okay, never mind.
So if there's something specific where you say, you know, I'm really struggling with this,
Could you review copper TDR dual trace
yep,
at least? Okay, that'd be great. Thanks.
yep. So not a problem at all. Okay, so what I'm going to do is I'm going to hit on my copper menu here. And I get a drop, oops. I get a drop down. The first thing I'm going to do is I'm going to take you through all the tests in the a la carte mode. So you want to do this testing. And so we're going to come up here. I'm going to click on the multimeter. And in the multimeter, you have 6 different test selections. And we're going to work those from left to right on top. We've got voltage AC and DC. We've got resistance. We've got opens, milliamps, and longitudinal balance and load coils. So I'm going to, and the 4 purple keys below the display, if you've got an ONX-580 there, I'm going to refer to those as F1, 2, 3, and 4. So everything I talk about when it comes to copper testing is balance, balance, balance. If you don't have balance, you're fighting an uphill battle on your cable pair. The very first balance measurement that you're going to make actually is 8 volts AC. So since you don't power with AC, you don't do a whole lot with AC except make a phone go ringy dingy. Why on earth would your company want you to test AC? Anybody?
For foreign voltage?
Well, foreign voltage, yep. But really, it's a safety thing first and foremost, to make sure that you have not plugged into a line or clipped onto a line that's been energized and you didn't use your little orange carrot top, or I'm going to date myself back to my technician days, the B voltage tester or whatever you're using out there, to make sure that all those things, you know, that you have are up, you know, are working. But we do have a 313 volt cutoff. So if we see over 313 volts, you're going to get a high voltage warning and it's going to shut the test down instead of burning the test set up. So anybody know how much? So when we look at foreign voltage or AC or induction or whatever you want to call it, you have to understand, since this is AC based, alternating current, it is going to induce itself onto your cable pairs. So with it inducing itself onto your cable pairs, how do you keep AC and foreign voltage off? How do you keep it out of your cable pairs?
Grounds.
Okay, that's only 1/3 of it. So bonds,
Shield.
grounds, and shields. You have to have all 3. You just can't sit there and ground to something. So you've got to have all 3. And if you've got good bonds and grounds, now when you all go out there and you put your bonds on and you put your grounds on, how many of y'all are using torque wrenches to torque those to the proper 35 or 40 psi settings? Because if you're not, chances are you may look like you're bonded and grounded. If you over torque it, you're going to remove that capability. If you're not torque tight enough, you might not have anything. So I always tell technicians, look at whatever bonds and things you're using and make sure you're torquing those things down to the right thing. This is not just a hand tight and give it one good, one more turn. These things are very specific to make sure that you maintain that integrity. So if we've got good bonds and grounds, that's going to get rid of about 90+% of the foreign voltage that's on there, or induction as you want to call it. How do you get rid of the residual that's left over? because there's always going to be something left over. Anybody? Through twisting of your cable pairs. So when you twist those cable pairs, what you're creating is an inductive field over top of a capacitive field. So if you look at your, there's a lot of different states here. There's a lot of folks on here for this call. But if you look at the PUC specs, the PUC specs probably say that you can only have 1 volt of AC across tip and ring. I truly don't care how much you have across tip ground, ring ground, as long as they're equal or off or off by a couple tenths of a point. So let's hypothetically say, hey, I've got 0.01 here, so that's good. There's no foreign voltage there. I go down to my tip ground, ring ground. Oops, that's not. There we go. I think I see the problem. Okay, I go down here to this, and I pick up 1.4 volts there, and I pick up 1.4 volts there. So here's the hardest math equation I'll give you for today. So one of these is negative, even though it's not depicted as a negative number. If I had 1.4, a positive 1.4 and a negative 1.4, and I add them together, does anybody know what I'd get? 0. They cancel each other out. So the twisting of your cable pairs is going to create this positive negative thing, and they're going to cancel each other out. Now, let's hypothetically say I had 4 volts across tip ground and 3 volts across ring ground. Could you live with that as a technician? What do you think? Anybody? Bueller? The answer is no. No, because what you're telling me is that's a 25% delta between tip ground and ring ground. So with a 25% delta, that's already telling me your pair is unbalanced. There's we don't know what it is yet, but I already know I'm facing an uphill battle. So that's the benefit of testing for AC. Number one, it's safety. Number two, it's the beginning of your balance measurements. Hopefully that makes sense. Now, if I come down here to bottom and I click on DC voltage, now DC voltage is direct current. It cannot induce itself onto the cable pair. Scream as you might think it cannot, because direct current cannot do that. So now, any measurement that you run has got to be run to an open cable pair on both ends. You cannot test into a DSLAM port. You cannot test into office equipment in the CO or a channel service unit or anything else like that, or a customer DSL or a channel service unit or whatever the case may be. All of these things that you have signatures. They have a termination, whether it's an AC or a DC termination on there, whether it's impedance or it's ohms or whatever it is. They've all got signatures. So you want to make sure that you open on both ends. If you don't know the state of the far end, and you don't know really what's happening out there. So in this case, if you've got the pair open on both ends, I'm not expecting to see any DC voltage. If I do, that means I am crossed to something, whether it's on my tip to ring, my tip to ground, ring to ground. If the pair's open, again, I'm not expecting to. If I am crossed, then we're going to use the RFL to figure out where that cross is, if it's cross battery on there. So does that make sense on AC and DC?
Yep.
Okay. Any questions or any gray areas before I move over to resistance?
Hey, this is Sean. I have a quick question. I see on your display that it says there's a 100K ohm termination. Is there a difference between the 1 meg and the 100K in terms of measuring for voltage?
You can pick either one. The reason we default to 100K is the old test boards that people, the old test boards, MLT and things like that, those were all 100K terminations. Most,
Okay.
And again, it's really whatever floats your boat. You just have to know that if you're doing DC voltage and you put a 1 meg termination on there, and let's just say let's say you have a regular INR technician out there, and he's got cross voltage, and his job is not to do an RFL. It's not in this job category. He hands that off to cable maintenance. I'm just making things up as I go here. And he tests this with a 100K termination. Cable maintenance, so he's going to have certain amount of voltage tip to ground, ring to ground for that cross battery. If somebody else comes in behind him with a 1 meg ohm termination, his tip ground, ring ground is going to be a different voltage value because of that termination. Does that make sense?
Yeah, that does. Thank you so much.
And then the technician and the cable maintenance technician is like, what on earth was he looking at? This is not the cross. I see the cross battery, but it's not what I'm seeing. It's only because you have different terminations. So we default to 100K. If you want to make it 1 mega ohm, whatever floats your boat, it doesn't really matter to us. So that answer everything. Can we shift over to resistance, or we still got more questions?
That's it for me. I feel covered on that.
No problem. Okay, thanks. So next thing we're going to do is we're going to come up here to the right, and I'm going to click on resistance. Now, your cable pair, contrary to popular belief, is not a resistor. In any way, shape, or form is it a resistor. It's not. What it has built in is series resistance. That series resistance is the inherent cable gauge that's on there and the inherent length of that cable. So the longer the cable, the more series resistance that's going to be there. Now, one of the things that I get technicians that they like to do is if you're a former Dynatel user, or you're a former you had a Fluke 990 Copper Pro, or you're a Sidekick person, or you've got somebody's going to take their test set and they're going to stick it on resistance, and they're going to do a stare and compare, and they're going to tell me, hey, I'm getting a different resistance reading than what I get on my former test set, the one that is tried and true to me, the one I know works. And I'm like, absolutely. But what I explained to them is there is no ITU, ANSI, Bellcore, or Telcordia specs on how to measure series resistance. Now, if you were to measure a resistor, we would all measure a true resistor exactly the same, minus a couple tenths probably. But series resistance, everybody has their own pet way of doing things. We think our ways gives very accurate readings, but so will somebody else. So, and the same thing on the opens meter. There are no ITU specs on how to measure opens. We all do it differently. But what I tell people is you're going to be somewhat close and in the ballpark. But if you do a stare and compare, you will see different readings. Now, I've got a test box here, and my test box is, is always going to read 999 unless, unless I put a short or something on there. So when you're out in the field and you're looking at series resistance on an open cable pair, the chance of you getting 999 is slim to none, and slim is out of town. But what you ideally want to see is something in the hundreds of mega ohms. So, if I've got hundreds of mega ohms, life is good. When we look at tip ground, ring ground, plus or minus about 15 to 20 percentage points. There's a lot of different things, splices, impedance mismatches, because somebody used a pick-a-bond, or somebody used a Scotch lock, or somebody used a bean on one side of a splice versus another, versus maybe it's an old 3M 25 pair splice, and there was a one side open, they found it, and they put a pick-a-bond or a Scotch lock or something on there. And if they put two pick-a-bonds on there, hey, my impedance would be the same. But if I left the one side on the 3M and everything, then I would have this impedance mismatch that, your tip to ground, ring to ground are never going to be the same. There's just too many things out there working against that. But again, 15 to 20 percentage points. Does that make sense so far? Now, one thing that you want to make sure that you do, if you have an ONX and you've got your ONX in front of you, what I always like to tell technicians to do is take all 3 of your leads and short your 3 leads together and make sure that you've got 0 ohms. So I've got 0 ohms across tip ring, I've got 0 ohms across tip ground, and I've got 0 ohms across ring ground. Now, if you have not compensated your leads in a while, then you're going to be off 1 or 2 or 5 or 37 ohms, which is going to just exasperate itself down the cable pair. So on the ONX-580, the bottom right button is what's called the tray key. If I press the tray key, the F1 key will say compensate resistance. Hit compensate resistance. I go ahead and hit compensate here, and it'll take about 10 seconds. It'll compensate that. And it says, hey, we're done. It gave me my date and time. I can go back and I can run all those tests again and make sure that I'm at 0 ohms. Now, chances are you probably won't have to do that about every 6 months or so. But if you're getting really funky readings and something's not right, you might want to just take a quick peek and make sure, hey, am I all zeros? Now, when I run series resistance, I always run it in the leakage mode. So a standard ohm meter, like we're doing right now, is mine or my competitors is typically 30 volts. The F4 key down below says leakage. So when I go to leakage is now applying high voltage. It's 120 volts. Now, it's not going to shock you. It's not going to damage the equipment because we are current limited. The current is what does the damage. It's not the voltage. You know, if everybody looks at a stun gun's got 1 million volts. It doesn't kill you, just makes you puts you on the ground, makes you wallow around like a fish out of water. But I like to hit it with leakage. I like to hit that cable pair with a little bit more voltage to see how it reacts. Our auto test will be done with leakage on there. Now, anything from 0 to 999 ohms is bad. If you're looking at an open cable pair, that means you've got a hard short or something else out there, depending on the length of the cable pair. If it has a K next to it, it is bad. That pair is not going to work. If you try to pass it off, you are guaranteed a repeat, or you may not even be able to get that thing to work. So you're looking for something in the hundreds of mega ohms. The ITU, the FCC spec and the every state's PUC spec is 3.5 mega ohms. That goes back to Alexander Graham Bell's days. And we didn't have ohm meters that would go above 3.5 mega ohms. So ideally, you want something in the hundreds of mega ohms. So I cover the Micronesian islands out in the Western Pacific, and I go out to Guam every few years. And I was in Guam a few years ago, and we were working on an xDSL T1. And I had 657 mega ohms across tip and ring. People said, that's wonderful. It's in the hundreds of mega ohms. Yep. Had 640 mega ohms across tip ground. That's beautiful. It's, you know, and I had 197 mega ohms across ring ground. They said, that's beautiful. And I was like, wait a minute, guys, that's 300% difference. I said 15 to 20 percentage points. Now, 197 mega ohms is out of anybody's RFL spectrum, because RFL stop at 20 mega ohms. They can't see anything above that high resistance. So we had to walk this thing, and we were walking this cable along the edge of the coast right there on the seawall. And we got into a 3M. We lifted up the rubber boot, which was half off, and this 3M splice was just caked in salt from the salt air. So we found our pair, we cut it out, we respliced it with a couple of Scotch locks, and it went up to 640 something mega ohms, and that xDSL T1 came up and worked. So when I say hundreds of mega ohms, whatever your tip ring is in hundreds of mega ohms, you want your tip ground ring ground to be within 15 to 20 percentage points. Does that make sense?
Yeah.
Is there any questions on resistance or series resistance that I can answer? That I
What if
haven't
you
covered?
have, what if you have active dial tone like 54, volts?
Oh,
Can you
can't-
still do this
No.
leakage?
No. I mean, you can still do leakage, but you got to understand when you're clipping on there with dial tone, so you're putting 100K termination on that dial tone, or whatever you're doing here to make this measurement work. So again, this is always done to an open cable pair. There's no point in making these measurements unless that pair is open, unless you're just trying to measure the DC voltage that's on the pair to make sure that, hey, I've got a neg 52 volts coming in, or I've got however many for a T1 or an xDSL T1 or whatever type of circuit it is. But all these measurements need to be done to an open cable pair, because now you're double terminated with whatever the CO termination is and whatever your test set termination is to make this measurement. Did that answer your question?
You got it.
Okay. Next thing we're going to do is we're going to cover opens. Now, I'll ask this question up front. What is your what have you been taught? What is your most accurate opens measurement? Is it your tip ring or your tip ground ring ground?
I've always looked at the ground and ring to ground, unless
Okay.
it's been straight across the pair, then the tip and ring is going to be pretty accurate.
Okay. So if you go by tip ground ring ground, hold your left hand out and smack it good and hard with your right hand and say, dag nabbit, somebody taught me wrong. It will never be your tip ground ring ground. From a physics standpoint, it's impossible. So your tip ring is how your cable pair is manufactured. Your cable pair is manufactured to 0.083 microfarads per mile. Does anybody know what a farad is, a unit of measurement of? Capacitance. So your cable pair is not a resistor. Your cable pair is a capacitor. That's all it is. It's just a long, skinny capacitor. If you look up the definition of a capacitor is two plates or two conductors surrounded by a dielectric insulator. Last time I looked, the cable pair is two conductors surrounded by a dielectric insulator. So the only way to hold a standard is cross tip ring. There's two things working across not being able to hold a standard to tip ground, ring ground. Number one, the different types of insulation, air core, pulp, jelly, whatever it is, 2 pair, 5 pair, 6 pair, 12 pair. They all have a different insulation value to ground. The second part of the equation, which really trips up the using the ground issue, is your soil resistivity. I don't know what state you're in, but whatever state you're in, I'm in the great state of Texas. So we have coastal land, we have mountain land, we have prairies out here where I'm out in the middle of nowhere, West Texas. So everywhere I go in Texas, there is a different soil resistivity. So I can't hold a standard to ground if I don't have the same soil resistivity or the same type of ground field. Does that make sense? So what I'm going to use my tip ground ring ground for is I'm going to make sure my pair is capacitively balanced. So right now I'm at air core and I'm 1779 across tip ring and I'm 1602 across tip ground and I'm 1601 across ring ground. The tip ground ring ground is plus or minus 5 percentage points. So we're doing good. So we're very balanced here. Now, I know I have some holdouts there saying he don't know what he's talking about. I'm going to use my tip ground ring ground because I've been doing this for many years and I know it works. So I'm going to do a little change here. I'm going to go down here to my F2 option key. Let me go back up here to where I'm at tip ring. And I'm 1779. And I'm going to change this to, instead of air core, I'm going to change this to jelly filled. So I'm going to hit jelly filled right here. And I'm still going to be 1779. Now, instead of being 1602 and 1601, I'm going to be 1480, I think 3 maybe, 1383. And I go down here to ring ground and I'm 1383. If I change this to a 2-pair drop, I'm going to be around 1240 here, probably. 1240. 1240, but I'm still going to be 1779. So my 1779 never changes, but depending on what type of insulation you have and what type of ground field you have, your tip to ground, ring to ground values are going to be different because you have soil resistivity and there's no spec to it in your fill type. But even at 1240, it tells me the pair is capacitively balanced. Does that make sense?
Are you connected to a half ringer on that tip to ring? Why is it longer than tip to ground and ring to ground? Are you seeing some sort of capacitor at the end of that pair?
This is my test box.
Okay, so
I've got a Tempo Greenlee FLS
so it's
1150.
seeing the capacitor at the end or the half ringer at the end of the loop.
Yeah, there is no half ringer in this box.
Okay. So why would across the pair be 500 feet longer than tip to ground and ring to ground?
It's just the inherent. It's again, it's the inherent thing of the air core versus jelly versus the type of ground that's in this box. I don't have dirt in this box. It's just the DC ground that it's working from. So it's not perfect, but it's it works.
I mean, sometimes we used both tests and I don't know. You say one's better than the other, but it's nice to know, like when you go across the pair and you see that distance being longer, chances are you're hitting something in the EBN or a capacitor or a set. And then when you go tip to ground, ring to ground, that's probably generally where the pair might be going to before the drop and the things are terminated.
True.
So it's kind of nice to have both,
Yep, but they're tip to ground, ring to ground is not going to be the same as your tip to ring. It may be very close.
Absolutely. Correct.
You're right.
Yeah.
And if you're used to picking up half ringers and ringer equivalents and things like that, those are all good things that you've keyed on over the years. So let me ask another question here. Let's say I had 4 25 pair cables, 26 gauge, 24 gauge, 22 gauge, and 19 gauge. They were each 5,000 feet long. So I got them strung down the road a mile, basically, and I get on the white blue of each pair. Is all 4 of those going to measure something close to 5,000 feet?
Probably not with the gauge difference, no.
Okay, got to remember this is a capacitive measurement and not a resistance measurement. It's all 0.083 microfarads per mile. So yes, they're all going to measure something around that 5,000 foot mark.
But depending the makeup of the cable, you could have a cable pair that's on the inner core of the cable. You're saying white blue.
I'm picking the white blue on all 4. So I'm being very specific. So the white blue in cable pairs has the most amount of twist. The red slate has the least amount of twist. The other 23 pairs, I have no idea what order they go in or what their twist rates are. But if I get on the white blues are the white blues. I'm going to measure something close to 5,000 feet.
That's correct. Yeah,
so gauge will make no difference whatsoever. I was a technician with I've been here for almost 28 years. My prior 16 years, I was with AT&T and Bellcore, or Bell Labs as it's called. Telcordia now. And when I was a technician, when I got into being I was a special needs technician, special services, I didn't understand opens meters because I didn't understand how all 4 of these gauges could measure the same way. And none of my instructors could explain it to me. So when I finally went off to college, I asked one of my engineering professors on the first day, I said, "Hey, can I ask you a question?" And he said, "Sure." I said, I work for AT&T, but this is what I'm running up against. And he says, "Oh, great question." He says, I can tell that you've had no electronics training before coming into this class. And I said, "Nope." He says, "You're going to struggle." I said, "Probably," but I made my way through it. So what he told me was the 0.083 microfarads per mile, the way you maintain that in cable pairs is you have to separate the distance between the center core conductors. So if you look at 26 gauge has very, very thin insulation around it. If you look at 19 gauge, I like this. I got this from a technician about 15 years ago, has big honking thick insulation around it. So 19 gauge has a much larger center core conductor. They have to make that insulation thicker to separate those conductors by a given amount to maintain that 0.083 microfarads per mile. Does that make sense?
Yeah, but I was always told it was the ratio of copper gauge to insulation always remains the same. So the percentage of a thicker gauge 19 cable requires more insulation, but
Yep.
it's the same percentage as it is to 22 and 26 gauge, just the wires are thinner. So the exact proportion of, gauge to insulation is the same between all three cables.
Well, if you look at the thickness of the insulations, they're not the same. If you look at 26 gauge, 26 gauge has very, very thin insulation, whereas 19 gauge has very thick insulation.
Right,
And that,
because also the copper pair is also thinner too. So it's the rate, I don't know if I'm explaining it right, but the ratio of thickness of gauge of wire to the amount of insulation is the same in a 19 gauge because it's a thicker wire, thicker insulation, as it is
Yep.
to a 26 gauge cable, thinner wire, thinner insulation.
yeah, and we're saying
Otherwise,
the
the
same. We're saying the
potential-
same things.
But there,
And all we're trying to do is maintain that 0.083 microfarads per mile. So I was up in Twin Valley, Kansas, gosh, back in the late 90s. And there was a cable up in the air, aerial cable, and it was about 3.5, 4 inches in diameter. And the technician looked at me and says, "How many pairs do you think is in that?" And I said, "Depends on the cable gauge, but I'm betting at least 400 or 600 pairs." He said, "It's a 50 pair cable." I said, "Excuse me?" So I go up in the bucket truck, I take the boot off, and it's 17 gauge copper. So if you want to know what 17 gauge copper looks like, go to Best Buys and go back into the high-end stereos and look at the monster speaker wire. And that's what this stuff looked like. But it was put in back in the late 40s or after World War II. And I guess in Kansas after the 40s, there wasn't a whole lot of, places out there. So they needed something to get dial tone and stuff to go much further. So they put this 17 gauge in, but it goes right back to the same thing. Much larger center core conductor, much thicker insulation to maintain. And I did some measurements. It still was 0.083 microfarads per mile. Now with opens measurements, if I measure all 25 pairs with my opens meter, I'm going to get 25 different distances. Does anybody know why?
Because some conductors wrap around the outside of the cable and some conductors go straight through, so there'd be less distance to travel.
Now that's going to be a very, very small percent. They're all twisted at a different rate. So again, the white blue has more twist, so there's more inherent copper in there. The red slate has the least amount of twist. So the twist rates are going to govern those distances. And the spec is plus or minus 8%. It's usually about 2 or 3%, but it can go as high as 8%. So when you're looking at opens meters, every now and then I'll get this knucklehead technician that says, "Well, my Dynatel 965, that opens meter so accurate, I could go 15,000 feet and dig on it." And I'm like, "That's mythical and magical." I realize you liked your 990, your 965 or whatever you had, but opens meters are general ballparks. They're going to get you out in the general ballpark. They are not going to be something that you're going to dig on. There's too many inherent things working against you. So again, when I'm looking at this, hey, if I'm 1779 here, I'm 1602 here. And if I go down here to this one, even though I can't really do this on my box and make it look right, if I saw something like this, what would that tell you?
One-sided open.
Yeah, I've got a one side. I had to lift the ground off to make that work. I don't have a one side open switch on this box. But it's just telling you, hey, you have a one side open. Now, if you were set to air core and you were on air core cable, that one side open is going to be very, very accurate. It's going to get you out there pretty darn close. If you were set to let's say if I'm set to air core and I'm on buried cable that's jelly filled, then my one side open is not going to be accurate at all. Does that make sense? because the fill type and the soil resistive and the ground field is going to be different. It's going to mess it up. Okay, so hopefully that makes sense on your opens. Now, you always need to, if you're going to do a resistance compensate, go down and hit the bottom right button and do a opens compensate. Just means open all 3 leads, hit compensate, and just make sure that you get this thing so that when you lift it off, you're back to all zeros. So I'll go back here, back out of that, and I'm 0, 0 there. I was going to say, dang it. Oops, I need to compensate again. Sometimes it oops, let me recompensate that. Sometimes, most times it gets it on the first try. Oh, I know why. There we go. And just, you can, and just go through this little thing and about every 6 months or so and just verify that you're at all zeros. Okay, so we've covered voltage, we've covered resistance, we've covered opens. The
Why
next
does
thing
mine
we're
say
going
2 feet after compensate? Is there something wrong with that? Or?
you might need to just run the compensate a second time.
Okay.
Like I said, mine said 1 feet after I compensated it. And make sure your fingers are not touching the physical leads themselves when you're running that. Okay, oops, wrong button. All right, so now I'm going to jump over to milliamps. Milliamps is a lost art. When I was a technician back in the late 70s, early 80s, I'm dating myself, we had to run current on everything. Now I tell people my current measurement is my 1 out of every 5,000 technicians. Does anybody out there test for current?
No, unless you're a coin tech. There's no more payphones.
I was going to say, you still have payphones? God bless you. So again, and typically current is only measured between tip and ring. We had an instructor that worked for Windstream. They have this test lab, and they can do current to ground. So when we developed the ONX, they asked us to please put current to ground, and I'm like, it's an invalid measurement, but okay. We went ahead and added it for them, but your current measurements are only done across tip and ring. Okay, next test we're going to do is longitudinal balance. How many of you all run sidekicks and have run a stress test before? Anybody? How many of y'all know what a stress test is?
That would be the equivalent of the VIAVI longitudinal balance.
It is the exact same measurement, just different reading. So every now and then I get sidekick people and they said, well, we're going to run our stress test. It's better than your longitudinal balance. They're exactly the same. There's no difference in the test itself other than the readings. So when Belcor came out with longitudinal balance in the late 80s, what they did is we put 1,000 hertz tone across tip to ground, we put 1,000 hertz tone across ring to ground, and we measure the differential between tip and ring. And we measure the noise differential. So a noise you gotta remember, this is back in the POTS days. So noise for POTS is anywhere from 0 to 20 dB RNC. So when I say 20 dB RNC, I'm talking about decibels in reference to noise using a C message or a POTS filter. So back before that, we used this thing called power influence minus noise equaled balance, which is right here. So I've got 70 something power influence, 5. So I would have a balance of 65 here. So a balance greater than 60 is a good thing. And it's typically 60 to the mid 80s. You might hit a 90 on a good day, but chances are not. So when we do our longitudinal balance, we're putting 1,000 hertz tone across tip to ground, 1,000 hertz tone across ring to ground. We're measuring the differential, the same thing Sidekick does. And we're giving you a balance measurement that's greater, hopefully it's greater than 60. Now, Longitudinal balance is and stress, because they're the same test, is 100% based on having a good ground reference. If your ground reference is poor or you don't have a ground, the easiest way to know is I just lifted my ground. It's going to tell me greater than 100. Somebody says, hey, that's greater than 60. No, that's really bad. We're looking for 60s to the mid 80s. If it says greater than 100 or the high 90s, what it's telling you is you don't have a good ground field. Now, the F2 key here says ground reference. So if I come over here and I select ground reference, it's going to lift the lead just like you do in the old Sidekick, and it says, hey, I've got a 41 that's a very good ground reference. If I take that if I take the ground off and I rerun that test, it's probably going to be 103, 104. Oh, it's greater than 100. Oops, let me hit that again, sorry. 103. It says my ground reference failed. So what longitudinal balance is taking into account, it's taking into account your twist of the cable pair. It's taking into a lot of factors that you haven't tested for and things like that. So does that make sense? If you get below, they tell you 50, 50 to 59 is marginal and below 50 is fail. To me, anything below 55 and you're going to have an issue with. That's just me speaking out loud. I'm not talking about the spec and things like that. So does longitudinal balance make sense? Are there any questions? You notice the theme to all this has been balance, balance, balance. Okay, the last thing we're going to look at is load coils. Now, I know some of you don't have load coils in your plant, or so you think. Some of you still have load coils in your plant. Can anybody tell me what a load coil does? Why do you only put it out there for pots, although they do make load coils that you can use for DSL. Why load coils? What does a load coil do to a POTS line? Anybody?
Adds length.
Yeah.
Pardon me?
Adds length.
Doesn't add length.
It doesn't
It
boost
does-
the distance.
Amplifies the signal.
Nope. I asked that question because, like when I grew up in the telephone company, I heard, oh, they're regenerators, oh, they're amplifiers. No, these are analog circuits. This is the last thing we're going to do. So understand, POTS, if you look at the FCC and your state PUC spec, works to 1,500 ohms. How far? That's all it can work to. Before, how far is 1,500 ohms? Depends on the cable gauge. So at 26 gauge cable, 1,500 ohms is just shy of 18,000 feet. You can't load straight 26 gauge cable because you start loading after 18,000 feet. If it's 24 gauge cable, that's roughly 28,000 feet. 22 gauge cable is roughly 45,000 feet. 19 gauge is roughly 90,000 feet. So POTS can go anywhere from 18,000 to 90,000 feet, depending on the cable gauge or whatever mismatch of cable gauges that you have there. So I'm not extending the difference. I'm not going to amplify it because I'd amplify noise. You have to remember you're working on a capacitor, correct? Because that's what a cable pair is. It's a long, skinny capacitor. So when we look at this, what does a capacitor do? Anybody know?
It stores electricity and then
Yeah.
and then puts it back on the board.
Yes, stores and discharges, correct?
Yes.
So that's what. So at 18,000 feet, remember our noise that we talked about when we were talking about longitudinal balance is 20 dB RNC. That pair running parallel to the power lines is going to pick up enough noise that you're going to be very, very close to that 20 dB RNC. Now, are you ever going to hear 20 dB RNC? Absolutely not. Depending on how old you are, you're probably not going to pick up the Rice Krispie triplets on the line till around 27, maybe 30 dB. Y'all know who the Rice Krispie triplets are on your phone lines, right? Snap, crackle, and pop, noise, hum, and all those other good things. So When we look at that, you can't hear the 20 dB RNC, but all the dial-up modems and modems that you have out there are going to be dying on the vine after 20 dB RNC. How many dial-up modems do you all install these days?
None.
Oh, don't say that. That'd be a very incorrect. Every POTS line you put in, POTS, not VoIP, every POTS line you put in, chances are it has a dial-up modem on it, because that's how caller ID, call waiting, and call forwarding, and all those call tones work. They all work on modem tones. So you've got a dial-up modem sitting in, you've got a modem sitting in there that's using modem tones, and that noise, once it gets above 20 dB RNC, can start affecting those modem tones, where somebody says, hey, my caller ID works, but my call waiting's not, or vice versa, or something. So the first thing a load coil does, it does three things. It is a low-end pass filter. So it's going to take anything above 3,500 hertz and it's going to filter it off. So therefore, DSLs, T1s, and anything else that works in those higher frequencies aren't going to work. Now, the people that make load coils is Charles Industry predominantly. Charles Industry also makes a smart coil that will add the high frequencies in for DSL services. The second thing that it's going to do is a load coil by its very nature is an inductor. So I've got a capacitive field, I'm going to add an inductor. So any noise or any charge that I have stored, if you're using H88s at 6,000 feet or D66s at 4,500 feet, that load coil is going to discharge or alleviate or mitigate that whatever noise has been built up through that charge, it's going to be gone, or the bulk that's going to be gone. So it's going to quiet the line down. And then there's an electrical term called Eli the Iceman. Anybody ever heard that before? Eli stands for electrical circuits. Iceman stands for inductive circuits. There's a phenomenon that works on long distance circuits. In an electrical circuit, such as your telephone lines, over long distances, current is going to lag behind noise, or excuse me, current is going to lag behind voltage, which is going to create noise. It's going to get out of phase. So the load coils at each point are going to put current and voltage back together again. If it was a long distance inductive circuit, voltage would lag current, and you'd put capacitors in to bring those back together. So that's all a load coil is doing. It's simply a low end pass filter, getting rid of the high frequencies and trying to get rid of the noise through the buildup of capacitance. All load coil does. If we detect a load coil, we will take an additional 10 seconds and run a TDR in the background and give you the distance to the first load coil. TDRs are high frequency pulses, so it won't see beyond the first load coil. Now, if you test into a DSLAM, you test into a residential gateway, you test into a DSL modem, the DSL modems and the DSLAMs and everything are always going to show up as a load coil. Number one, it has a big honking capacitor inside there. So number one, when you run an opens measurement, you're going to have thousands of extra feet on your opens measurement, up 7,500 to 11,000 feet if you test into a DSLAM. About 1,500 to 3,200 is what I've measured into DSL modems and residential gateways. But they also have a POTS filter on them, so that your residential gateway has a place that you can plug a POTS phone into and get POTS service out of it. And if we see that drop in frequency, we're going to classify it as a load coil. A load coil detector test is not scientific. It's very simple. It's just a modem sweep, or excuse me, a tone sweep. We start at 300 hertz and we run a tone sweep up to 10,000 hertz. So if you put your butt set on it, what you'd hear is something that goes whoop. It's just going to run this quick sweep. And if we see a drop in that frequency, we're going to classify it. If we see a drop, we sit there and say there's a load coil out there. We don't know if it's a gateway or whatever it might be. Does that make sense?
Yep.
Okay, so that covers that. Okay, so we've covered the multimeter. Are there any questions?
I was just going to make a statement. I've had load coils come up as power influence.
There's no power influence in a modem.
No.
in a load coil. There's nothing there. Power influence is from the power lines, the AC induction.
What I'm saying is I measured load coil. It told me I had a load coil when it was just my drop next to the power line.
I'd have to see that one. I don't know. There's nothing in there to say why it would generate a low frequency drop.
Yeah, it told me I had a load coil. I looked up and it was 16 feet away. I looked up and my 2-pair drop was probably 6 inches away from their power line coming into the house.
Yeah. I don't have an answer for you on that. I don't have a good answer for you.
Okay, that's why I was kind of getting into what else could cause it to think it sees a load coil.
Yeah. Because all we're doing is a frequency sweep. We're just running a frequency sweep. If we see a drop in frequency, we're going to classify it as a load coil.
I got a quick question. So here in my area, we have load coils about every 6,000 feet.
Yep, H88s.
What would be the reasoning to that if it can go further than that?
So your load coils the way load coils are spec'd is they're spec'd to go if it's an H88, they're 6,000 feet spacing plus or minus 2%, plus or minus 120 feet at 6,000 feet. If you mess with that 2%, what you're going to do is that frequency that it's going to cut off is going to get way off. So all of a sudden, I've had people, I've gone out on troubles where somebody says, hey, the customer's phones aren't dialing out. The 369 pound key isn't working. And somebody says, well, they got bad phones. I was like, well, they're talking about all 4 of their phones. Well, all 4 of their phones are bad. Okay, what's the chance of all 4 phones 369 pound key? What it is, it's a misplaced load coil, and it's filtering the 1577 hertz on that 369 pound key because of the misplaced load coils. That's why you have things called build-out capacitors. You ever seen those or heard those before?
No.
So what a build-out capacitor is, let's say we're back in the 60s and 70s and they're loading cable plants, and you get out there and there's a big highway. It's got 5 lanes across one way and 5 lanes across the other way. And right in the middle of that highway is your 6,000 foot mark. And you've only got 2%. So there's no way you're going to meet that plus or minus 6%. So you go before that and you put a build-out capacitor in. And the build-out capacitor simply makes it where you put that build-out capacitor to make it look like it's 6,000 feet away.
Okay, so if you remove, like we have spots that have 4 or 5 loads in it. If you move one, that messes
you're going to have
it
a
all
mess.
up.
You're going to have a mess on your hands. Absolutely.
Good to know.
So does that make sense so far? Has this been helpful?
Yeah.
Okay. So I'm going to show you the easy way to test a cable pair, as I hate working hard. So I had 2 boys that work for AT&T. One of them took my advice and let me coach them and teach them how to do copper testing. The other one struggled mightily. So on your ONX-580, the very top menu, if you're up to date on your firmware, is called My Test. If you go down in there's a test called One Check Good Pair Test. Has anybody ever seen or run this test before?
Yes.
Okay. So this is going to run 30 measurements in 90 seconds. Now, folks, I'm going to tell you right now, that multimeter that we just did, you run 4 of those 6 tests, and you're going to be more than 90 seconds. And there's no pass-fail on that. So I really don't care when you're in the One Check Good Pair test. I don't care about your cable type, whether it's air core, jelly. You can put it to whatever you want. We always call mixed gauge 24 gauge. So I don't care. I just say, hey, pick whatever type of job that you're doing and set that, whether it's ADSL or HDSL or POTS or something else. In this case, I'll say VDSL. And when I start this measurement, again, we're going to run 30 measurements in 90 seconds, and we're going to give you pass fail. Put some troubles in here. So now it doesn't get any simpler than this, folks. It really does not. And we're taking the guesswork out of, hey, what's passing, what's failing? Because when I ride with technicians, one of the questions I ask is when they're running a test is, hey, what's passing or failing? Well, my gut tells me. I've been doing this long enough that my gut will tell me if this is going to work or not. Well, that's not the most accurate thing to use, but hey, we're trying to give everything to you right now. We're also going to check for things that you're not checking for. And when we get into the DSL world, all this is going to make sense. So if we look up top here, volts AC work fine. Volts DC, hey, I got a neg 2.78 on there, so it's marginal. Longitudinal balance failed. And if I come down to leakage, it tells me I've got 100K cross. And that's where that 2.78 of voltage is coming from. But it also tells me I have a bridge tap at 957 feet. So I know all this within the first 30 seconds of this test running. Now it's going to run a whole bunch of noise measurements. And so if I look at power influence is 80 dB RNC or less. 80 to 90, 80 to 89, excuse me, is considered marginal. Anything power influence over 90 fails, except if you're in single phase power. So I live out here on a ranch in the middle of absolutely nowhere, Texas. Before I got fiber, I am 4 miles on single phase power where the telephone lines parallel. My power influence was 107 or 108. I can't remember exactly which one it was. Now, a lot of people said, oh gosh, nothing's going to work there. Nah, I'm properly bonded and grounded and shielded. Everything worked just fine. And if I called the Texas PUC, they would say, yes, it violates the 80 dB RNC, but the telephone company has said that you're paralleling single phase power. 3-phase power, 2-phase power, 80 dB RNC is not hard to hold. So let's just go. So we've gone through these things. Leakage is your resistance measurement, and again, 100K. So anything with a K, you're dead in the water. That's why the longitudinal balance failed, because I've got cross battery on there. I've got 100K, so I'm not a very balanced circuit. There's a bridge tap at 957 feet. I've got 70 dB RNC for power influence. My circuit noise is almost 10. Remember, 0 to 20 is good. Now, the key things that you need to look at. Forget anything that has a U or a D. Those are the up and downstream bands of VDSL. Unless somebody has a ham radio operator out there and his equipment's not properly grounded and set up, and he keyed up his mic during your test, the U's and D's are not going to fail, but the F and G's are critical to you. It'll be the G filter 99% of the time, and if the F filter lights up, it'll light up with the G filter. If your G or F filter lights up, very simple. You have a bonding, ground, or a shield issue, or all three. It's telling you right now that there's something on, you're torqued too tight, or whatever the case, or you're not torqued enough, but you have a bonding, ground, shield issue. And I can guarantee we will see that bonding, ground, shield issue when we get into the DSL graphs and we look at the quiet line noise. And what we're looking at here is in the G filter, we're covering the entire AM radio spectrum. How do you keep AM radio out of your plant? Bonding, grounding, shield. Remove one of those three components and AM radio is going to go right on through your cables. It is going to severely affect your DSL circuits. So now I always tell people this is a check and balance. So if the G filter lights up, hey, you've got bonding, grounding, shield issue someplace. Where it is, have no idea. Just letting you know it's there. But we're doing a lot of measurements here in 90 seconds that you're not doing using a multimeter. We're also detecting if you have a bridge tap out there. Does that make sense?
I got a question. Yeah, yep. I've ran that test a couple times, and I know there's loads on it, and it'll fail and say it won't even do the load test. It'll just disappear, and then I'll run it again, same thing, and then I shut it down, restart it, and then the load, it will actually run that test. Is there a reason why?
I have no idea. That's the first time anybody's ever told me that. If there's a load, if we do a frequency run and we see a load coil, we're going to count how many load coils we see. I've never heard of it stopping and making the test disappear. And I have, if you can send me a test, a report with it, that'd be great. Just save the results after that test, but I've never seen that.
Okay, I'll try.
Okay. So this is, folks, this is the simplest way. If you want to cut if you've got repeats and you're, like my middle son, he had the highest repeats in his garage because he wouldn't do what he just wouldn't do this until he was getting in trouble. And he finally said, Dad, can you help me with this? So I'm going to go ahead and cancel out of here, but this is the single easiest way to test a cable pair. Go open it at both ends, run the good pair check in 90 seconds. If everything tests good, you're going to be pretty much good to go. Okay, so I'm going to drop back down here in the copper menu. I'm going to go over my TDR. Now, my TDR is second to none. We have so many patents on my TDR. We have some good TDRs, and we have a horrific TDR that I'll tell you don't use. Okay, so right now, when I'm out in the field, I will always start my TDR with a standard TDR. Now, there's a lot of inherent issues with the standard TDR. Number one, I have about a 26-foot dead zone. So I'll hit my mark here. I'll bring this thing out about 26 feet. And that up and down pulse that you see to the left there, that is the launch pulse. My other TDRs do not have a dead zone, but the standard TDR sees everything, and that's a good thing and a bad thing. So again, we have a lot of stuff. We put a lot of R&D into our TDR, and I'll go against anybody's, and I'm going to win every time. Up top, we have this thing called quick range. We took that from Dynatel. When Dynatel went out of business, we were asking technicians, what did you like? We love the quick range, double the range each time you go out. We found out Dynatel did not patent the quick range, so we thought, what the heck, we'll put it in ours. So down at the very bottom, if you look at the grid there, it says 250. If I hit that plus sign up there for the quick range, it's going to double that to 500, double that out to 1,000. I'm going to go out here to 2,000, and I'm going to see my open out there at 1,900 feet. So on this box, I have 1,900 feet of cable. If I take this and I move my cursor out here to the end of that cable, 1904 or 1899, 1895, I'm right there at, at 2,000 feet. 1899, I'm right on it. Now, move that cursor back out of there and get it out of the picture. So now if I take it and if I short this cable pair, I'll see a short on the end of that. It'll drop right down because this is the live TDR. And there's my short. So I can see this. Now, I have a gain feature down below. And if I click on that gain feature down here, I can take that open and I can blow that thing up. And I can get a little bit more resolution. But as I do gain features, what I also do is if you look between 0 and 500 feet, there's a whole lot of mess there, isn't there? And as I put gain in, I'm adding to the backscatter, distortion and noise and everything else in there. Now, I'll tell you on my test box, there's a splice at 250-ish feet. There's one right before 500, 480 feet. There's another one at 960 feet, and there's another one at 1,574 or 1,570 feet on my test box. But they're really, really hard to see, and these aren't normal splices. This is a circuit board that they've got things wired to in the back of my test box. Now, I'm going to drop a bridge tap on here. So I'm going to drop a bridge tap on there at 960 feet. So that's pretty easy to see. A bridge tap is a down pulse followed by an up pulse. And I'm going to drop a high resistance open, a bad splice on here at 1,470 feet. Now, let me ask you this. If you were to run this TDR right here, and this is what you got, could you make heads or tails of what this meant? And be honest. Anybody?
No.
Where would you go first if you had to look?
1,000
Probably the
feet.
bridge step.
Bridge tap.
Yeah, or that 500-foot mark. You know, that's a pretty big event there, correct? So what I'm doing is I'm using my sniping tool and making a picture of this that we can do a stare and compare with.
Yeah, but if you bring down the gain, you're still going to see the bridge tap, but that fuzzy stuff at 500 feet will look less.
Yep.
No,
absolutely.
So I'd probably still go after the bridge tap at.
Yep.
What is
Okay.
This, 1,000 feet? Yeah.
Yeah, but you're really left. What I get people to is you're really left scratching your head as to, my gosh, what is all this stuff, right? Now I'm going to hit the mode key. I'm going to show you the other TDRs. Under no circumstances, even attempt to use the in-home TDR. It is gosh awful. It'll just, if you want a really bad day and you want to make it worse, we developed it for British Telecom. It will tell you to twist your leads, and it wants a Cat5 type twist on your end of your leads coming off your test set, and it's still going to suck. The problem is we can't take it out of the test set because it's built into the main code. Either that or we would have removed it years ago. So I just tell people, do not use in-home TDR. If you want to shoot something inside the house, use Smart Gain. So Smart Gain is using 2 patents. So when I go to Smart Gain, if I lift my cable leads, I will see right on the end of my cable leads. I don't have a dead zone. So there's the open. If I short my 2 cable leads together, I see right on the end of it. Does that make sense? Remember, my standard TDR has a 26-foot dead zone roughly. This does not have any dead zone whatsoever. Now we're running 2 patents. One is called Smart Gain. The other one is called Time Varying Gain. Now, and there's one more in this field that we're looking at called Adaptive Pulse Code Modulation TDR. Has anybody ever heard of a step TDR before?
No, but could I just ask you a quick question about standard?
Sure.
So if you're in a buried service wire and you're in between pedestals and you got like say 200 feet or 150 feet, is Smart Gain a good way to test between pedestals, or that still should just be okay?
Nope. So let me explain Smart Gain for you here. So there are a couple of things that there's a lot of very good with Smart Gain. There's some negatives to it. Number one, Smart Gain and Time Varying Gain have patented filters built in, so we're not going to see splices. So that's why I run standard TDR, because I'm going to see the splices that are out there. In Smart Gain, I'm not going to see splices unless that splice is really bad, unless it's a super high resistance open, greater than 20 ohms. So, but right now in this first 234 feet, I am running a patented step TDR. Step TDRs are what electronic board technicians use to find problems on circuit boards. And those step TDRs are accurate to a millimeter level. My step TDR is not accurate to a millimeter level. At 234 feet, we're plus or minus 12 to 15 inches. So we're very, very accurate. The problem with a step TDR is step TDRs are not like pulse TDRs where opens are up and shorts are down. Step TDRs are transitions. So our old HST 3000 had a step TDR, and it was about a 2.5 to 3 hour course just to teach a technician how to read the different transitions that were happening. So David Weir, our senior, one of our senior engineers that did all of our TDR work, he converted the step TDR into a pulse TDR. So this first 234 feet is a patented adaptive pulse code step TDR called adaptive pulse code TDR. Now, we're accurate to about 15 inches here. So we're very accurate. So if you want to shoot something inside the house, or as you said, between pedestals, this is the way to go. Does that make sense? Now, if I come over here and I hit the plus sign, I'm going to take that 200 feet area and I'm going to double it to 400 feet. The adaptive pulse code TDR is done. We're now back to time varying gain and Smart Gain. So I'm going to just drop this and this, and I'm going to go out here to the end of the fiber, end of the fiber, 1900 feet, there's my open out there. Now I'm going to drop a bridge tap on here. Remember, I got the stare and compare over there to the left. So I'll put the bridge tap on there, and it makes a little bitty down pulse. So since I'm at 0 gain right now, because time varying gain and smart gain are doing their things, I'll just make this a little bit bigger. I'll blow the open off the top of the screen, but that's okay. There's my bridge tap. Now I'm going to drop that bad splice on there that I had. Now between those two, which one's easier to look at now? Or easier to figure out?
The smart gain one.
Yeah, the smart gain one's a whole lot simpler. So I can, and you notice there is no backscatter noise and distortion. All that stuff gets filtered off, but so do your splices. So I'm not going to see all those different splices out there. Does that make sense? And the fine tune that at the bottom that you see down there, that is your cable gauge. So if you if you know, hey, I know I'm 22 gauge cable, you could drop that down to 22 gauge. Most people don't play with it, and it does it in half gauge increments. And somebody says, why do you do it in half gauge increments? I don't know, because sometimes 22, 24 gets spliced into 26 or spliced into 22 or whatever it is. So we can just do that in half gauge increments, and you might get a little bit better granular results. Everybody okay with that? Okay, so the next one I'm going to show you is something called auto ID. So if I run auto ID, cursor is way off the page here. Yeah, I'll let it do its thing. Okay, so now this is the same thing as smart gain, except we're applying some artificial intelligence. And on my test box, my bridge tap is at 960 feet. And you can look that up online for the FLS 1155. It's made by Tempo Greenlee, the Sidekick people. So I missed my bridge tap by 1 foot. Not bad for 1,000, for close to 1,000 feet. My cable is 2,000 feet long. Hey, I got that at $18.99. I'm very accurate. Now, I did lie on the tap open. That is not a tap open. That is a high resistance open. Okay, so when we apply this artificial intelligence, everybody builds their cable plants a little bit differently. So that should have come up and just said splice on it. But on my test box, since I don't have real splices, it comes up and says tap open. So what I tell people is about 85%, 90% of the time, we get all those things right. But there's that, 10 or 15% where we mislabel something. In this case, we mislabeled it, and I'm as honest as I can be about it. It's going to happen. And what I tell technicians is whether we mislabel it, whether we nail it, it doesn't make any difference. You've got to go out there 1,470 something feet and find that splice or whatever it is and figure out, probably resplice it or figure out what it is. You're going to go out there 960 feet and figure out that, cut that bridge tap off. Does that make sense? And then there's one other TDR mode. Most people won't use it. It's the same as this. It's called one check. And what one check is going to do is it'll do your voltage measurements and everything, and then it'll do the auto ID. So if you wanted to run a quick check and make sure, hey, I went out there, removed that cross battery. Let me just double check all this, even though I still have the cross battery still turned on there. Telling me my longitudinal balance still sucks because I've got that 100K cross and the cross voltage out there, but I still get all my events like I'm supposed to. Does that make sense on the TDR? So somebody said they wanted me to talk about the, let's see, the dual trace TDR. Is that correct? I thought somebody asked me to talk about dual trace.
I heard somebody say that earlier.
Yeah, I did. Yeah.
Okay. So dual trace is not going to work in auto ID or one check. It'll work in time varying gain or in
Standard
or smart gain.
Yeah.
So now if I do dual trace on here, if I come in here and I say dual trace, what this is going to do is when I run this TDR, even though I don't have a second test box, it's going to put, so now you can have two cable pairs. So if you had a good cable pair and a bad cable pair, you could actually physically do a stare and compare. And say, okay, my good one is my first pair, that's in orange. My bad one is in blue. In this case, I've got an open at about 5 feet. But that's what the dual trace does.
Does it factor in the information from the good pair to adjust on the bad pair, or it's just no?
They're two totally independent TDR traces. It's not doing any comparison. It lets you do that comparison. As I tell people, if pair 1 is working fine, like if you're looking at a DSL circuit and pair 1 is running fine and pair 2 is running errors, then you can kind of, if it's a tip ring type issue, high impedance or low impedance, then the TDR is going to pick that up and you can see that difference between the two.
So for our bonded services.
Yep.
Okay.
Or if you're out there and you've got, hey, this is my pair. Let me try this other pair. Let me see if it works any better. It just allows you to do a stare and compare between two pairs. Make sense?
Yeah, that makes sense.
Okay. I'm going to bounce out of TDRs and I'm going to go into RFL testing. Now we've got a wicked cool RFL. And depending on which ONX-580 you have, I have an ONX-580. There's also an ONX-580P. The difference between the ONX-580 and the ONX-580P, there's about $1,000 price difference. In my RFL, I only have a single pair RFL. In the P, there is a second pair RFL. I will never ever use a second pair RFL. That's why my unit's just a single pair. There's no need to do a dual pair RFL. And somebody says, well, and your argument's going to be, well, what happens if both my tip and ring leads are bad, and I have to use a second pair? Still do it with single pair. So I've written 3 white papers on this over the years. I had Frontier up in Rochester, New York, your training center that was up there many years ago. And they had the ONX-580 and they were saying, oh my gosh, we have to have this second pair RFL. And I was like, no, you don't. And I sent them the white paper and they said, no, this is still not going to work. And I actually went up there and met with the folks. I can't remember. It's been probably 10 years. It's probably been 8 or 9 years ago. And I said, all right, let me come up here and I've got to come up in the area anyways. I stopped by and I said, all right, let's run. I've got an ONX-580P here. Let's run this and see what we get. Okay, we got this. And I took the same unit, went to single pair. And what I explained to them is the RFL tester is only using 3 leads. It's using a tip ring ground lead. Even though you're hooking up the second set of leads, we're either going to pick up the tip. We're going to pick up the tip side, the second pair that you're putting the yellow blue on, and the ground. But we're only going to reference 3 leads in this whole thing. And so when we ran it the second time, I think there was like a 1 foot difference. It wasn't any more than a foot difference after we ran 3 or 4 tests. And he was like, oh my gosh, this works. And I said, yeah, I picked it up from an AT&T technician about 20 some years ago when I was out riding in the field, because I'd never heard of it doing it that way. So single pair, there's something called a K test, which you'll never use. It's a big German word. It doesn't work. You can try it, but it's never going to work for you. It's a difficult setup at best. So, but we put it in there because our competitors put it in. Okay, so on my RFL, what I always tell technicians is check your RFL before you run any type of test. Check your RFL and make sure it is calibrated. The simplest way to do that is short all 3 leads together. You can't do this on anybody else's test set and run an RFL real quick. So I've got all 3 of my leads shorted. That means up there where it says DTS, distance to strap, distance to fault, distance to strap to fault, and the fault size should all be 0. 0 ohms, 0 feet between those 3 leads, where that short is. You were breaking up there, Todd. I'm sorry.
Sorry, I got a question. I don't have the RFL on here. Is there a way to get it done?
Yeah, you and I talk offline when we get done here.
Yeah, cool.
So RFL takes about a minute, 20 seconds or so. What we're doing is when we do an RFL test, so now as you can see on my unit, I'm all zeros up there, correct? There is no need for me to do a compensation. And I am very strict on this when I'm in the field riding with technicians. I will always do this measurement first before we start running any RFL for the day. I never assume, because if I get off by 2 feet or 3 feet, that 2 feet or 3 feet is going to be very logarithmic down the cable pair. I could be off 1,000 feet from where my trouble is on down the line with just a few foot difference. So I always do this just as a quick double check. Let me hook back up to my test box and put my ground fault on, take these two guys off. So what we're going to do is we're going to strap this. And again, if I had a separate pair, all I would do is take the tip from my one side and the ring from the other side, and I would strap those two together, from tip from one pair, ring to the other pair. That's how I do this single, and then put the ground on there. I try to make, my white paper defines it very simply, but you're only using 3 leads. Okay, that's off, that's off. I got a ground fault on there and I've got a short on there. Okay, so we're gonna run this. On my test box, my fault is about 490 feet. So I've got the house is sitting at 74 degrees. So we'll see how close we get. This box is 24 gauge cable, so it says. If you looked inside there, I really wonder what type of cable it is. It's definitely 24 gauge, but it's not your outside plant cable. But like I said, the box works real well. I've been lugging it around for 20 plus years, and every now and then I got to take it apart and resolder something on the circuit board that stopped working. And it'll come back and tell me my fault's not on my red lead, but it's still going to give me my readings. All right, come on now. Well, you are taking a long, long time. Okay, something didn't work. Right? I was saying that's taking too long. Let me try this again here.
When you're running this test, you need one side to be completely clean and the other side to be a pretty much solid trouble. These aren't for high resistance troubles.
Yes, I need 100 times difference between the
100 times difference.
100
okay.
times difference. So maybe one conductor's, not as bad as the other conductor. As long as it's 100 times difference, life is good. Does that make sense?
Yeah, kind of. I just know that when I'm doing
so
this,
let's say you had 100
I want one side of that pair to be really clean, and sometimes what we'll do is we'll have a guy at the other end show him a short and say, okay, well, that side's good, and now we go to the pair that we know is bad, and we figure, well, that's not a solid enough trouble, so we go and look at another cable pair that might be more solid and use that.
Yeah, so RFL is 100 times difference. Sorry, something hung up on my RFL. Let me try this again here. Let this thing initialize, and we'll start this test again. All right, let's see what happens now.
What does 100 times mean? Like, so if you have
okay, so let's say you had let's say you had 1,000 ohms short on there.
Right.
You're going to need something that's going to be at least 100K or better.
Okay.
Does that make sense?
Not really. No.
So let's say you had 100K. Let's say you had 100K cross. Excuse me.
Okay.
Or excuse me, 1,000K cross.
Okay.
On one conductor, let's just say tip to ground. Okay. What did I not turn on? Oh, I didn't turn on. That's what the problem was. I didn't have the ground fault on there. I put cross battery on there. Darn it all. So let's say you had 100K. Let's say you had 1,000 ohm cross. All right, on your tip conductor. That means your ring conductor has got to be greater than 100,000 ohms. 100 times difference.
It needs to be a clean pair.
Yeah. Now, understand, the higher the resistance, we can measure up to 20. We can measure up to 20 mega ohms. But at 20 mega ohms, you're probably only going to be we're probably only going to see about 1,000 feet. We're not going to see very much, much past 1,000 feet. Okay, so now it comes back and says, hey, it's not on that one. It's not on the red lead. I could rerun it if I wanted to, but I don't have to.
So the RFL is better troubleshooting on shorter cable pairs rather than longer.
Well, so if you've got something in the hundreds in the kilo ohms, you might, depending on the cable gauge, you might get 6,000 or 7,000 feet. So RFLs are not, mine or anybody else's is not going to shoot long range. These things aren't going to go out 15, 20,000 feet.
Okay.
So when you shoot an RFL, if you're not getting a reading, you need to move closer.
That's understand. Yep.
And then and what I tell people is you're never going to do this off the first measurement. You're always going to keep moving closer, because chances are you could have multi-gauge copper out there, and then that's going to mess things up. I have got something else turned on in the box that I can't figure out.
Yeah. So we got 12,000 foot F1s out here from the CO to the cross box. You're probably going to go somewhere out about 6,000 feet, cut it in half, and cut and prove and look both ways. Now you're down to like 6,000 feet in each direction.
Exactly. And as you move closer and closer, sooner or later you're going to overshoot it and you're not going to get a reading. Okay, I've gone past the problem. So really what I always try to like to do is I like to get within 300 to 500 feet of the trouble, because then I know I'm pretty much probably on the same cable gauge. I'm on one cable gauge. There's probably not going to be a cable gauge change in that next 300 to 500 feet, or at least I hope. And then I can do this, and that way it cuts my distance down, and now I know what I'm looking at. So in this case, it tells me I'm 510 feet out there. Okay, so at 2,500 feet. So I would want to. I can't do that on this box. I would want to move closer on this to get that, to get down that, because I know my box is 490 feet. So I'm off by 15 feet at 2,500 feet. That's not too bad for the first shot out there. Does that make sense?
Yeah.
So I just tell technicians. Pardon me?
When you know where your trouble is to start with, it makes sense.
Yeah.
But I know what you mean. You just gotta. It's just another bullet in the gun, so to speak, to try and, because you got to use your percentages, and then you got to drive the length of the cable. It's just all another tool on how to get on top of the trouble that you need to get on top of.
Exactly. Okay, so was that good on the RFL side of life? So on the copper side of life, has this been pretty good? Have you all picked up some tips and tricks?
Okay. I have a quick question about the RFL test. So believe it or not, I heard it's actually possible to RFL shorts only if you have another cable conductor pair strapped.
Exactly.
So
if you have but a TDR would be much faster on a short than an RFL would.
Mm-hmm. So for let's say we have like an 800K short, a really light short, and it's on 40,000 feet of F2, and even then it seems like trying to TDR that really light short, you're going to be blue in the face trying to isolate it on a TDR.
And you're even going to be worse at 40,000 feet trying to do an RFL, because that RFL is not going to reach out that far.
Okay.
You're going to have to keep dividing and conquering to get closer to that problem.
Okay, makes sense.
And you may have to move your strap backwards too, because if it's if you're out there 10,000 feet and you're doing a 40,000 and the strap's out there 40,000 feet, you're still never going to see it. So you may have to cut the pair in half and strap it there, and do that first, however far. but you know, TDR is probably going to be a lot easier on that. But again, yes, you can do shorts on that. Absolutely.
I got a question. So your to strap says 2,500 feet, but your cable is only 2,000 feet. Where's the extra 500 coming from?
That's because I put that 2,500 in on the last job I was doing, and I didn't take it out.
Oh, okay.
Yeah, I was out in the field with my local service provider last week, and I didn't, or last Friday, and I didn't take. We were shooting it, and we knew what the strap size. We knew what the strap was.
Okay, that answers that. Thank you.
Yep. Yeah, I got to take that out. So I'm going to move on to DSL if that's okay. Was this good on the copper side? Did y'all? Hopefully, you picked up something.
That RFL won't work with any voltage on the line, correct?
Yeah. Well, so you may have voltage on the line because you've got cross battery. So yes, it's going to work. Because if you're shooting across battery, you're going to have battery on that line.
Okay, thank you.
All right, and something really went wacky on my computer. Hold on a second. I got to switch gears and change my view over to screen 1 instead of screen 2. All right. Stop sharing. Share. Screen 1. Move that out of the way. Okay. So let's talk about DSL. So there's a lot of different types of DSL. We started out with ADSL back in the late 80s, moved to ADSL 2+ in the mid 90s. We've got xDSL T1. We've got G.SH DSL. Symmetrical Ethernet circuits. You do a ton of RDSL. Nobody's ever told you, but you do. Take my word for it. You also do VDSL 2 and 2+. And in some areas, some of you may be doing the G.Fast or G.Fast Amendment 3, which is 112 megahertz. So whatever you're doing, my question to you all is, all of these different types of DSL circuits that you see, are these DSL circuits analog or digital? What have you been taught?
Digital.
They're 100% analog. There's nothing digital in DSL at all, except for the name digital. So number one, the first dead giveaway is you're installing a DSL modem, correct? What's a modem do? Modulates, demodulates. So we're not doing digital circuits. Okay. Now, the first, second, and the fourth column are the most critical here. So ADSL has an operating frequency of 25 kilohertz to 1.1 megahertz. The fourth column there says you have 256 bins. Think of those bins as submodems. Each submodem is 4.3125 in kilohertz. A dial-up modem is a 4 kilohertz modem. It's the same thing, except these are nailed-up modems. They're not dial-up modems. So if you had a dial-up modem, you might be able to get 53 megs or something like that. With ADSL, you have 256 submodems, which means you can go much faster. You have 256 more modems, or 255 more modems over a dial-up modem. Some of those modems are dedicated to upstream. Some of them are dedicated to downstream. ADSL 2+ doubles that frequency to 2.2 megahertz, which means I double the amount of submodems I have to 512. Now, as I start to go up in frequency, my speeds go up because I have more modems to work with, correct? But what happens to my distances? Anybody?
Your distance gets smaller.
Yeah, the distance gets smaller. So I may have gone from 15,000 feet at ADSL to 10,000 feet on ADSL 2+ at 26 gauge copper. When I go to VDSL 2+, there's only two working ones that you all deal with, and that's an 8 megahertz or a 17 megahertz profile. So at 8 megahertz, there's 1,960 submodems. At a 17 megahertz profile, there's 4,096 submodems. So all of these submodems, so my DSLs get faster, but they get shorter. Now, I could do 50 megs on VDSL. I can do that on an 8 megahertz profile. I could do it on a 17 megahertz. Loaded question for you. Which one would be easier to do it on? 8 or 17?
17.
17, I got more modems to work with, right? But which one's going to give you better distance?
The 8 one.
The 8 one. So it's, you got this balance beam there that you're trying, that the DSLAM's trying to figure out, hey, do I give this to you as an 8 meg profile or do I give this to you as a 17 meg profile? The DSLAM's doing a whole lot of accounting trying to figure out what to do here. Does that make sense? Now, this one's always a kick in the gut for everybody. DSL is a 125-year-old technology. It is not new and the latest and greatest thing. It goes back to Alexander Graham Bell's days, where we use something called frequency division multiplexing. And that's all we're doing here. We're taking that 1.1, 2.2, 8 megahertz or 17 megahertz, and we're simply dividing it up into frequency division multiplex channels. Each channel is 4.3125. Now, that sounds confusing. It's the same thing as an FM radio dial. So your FM radio dial that you listen to day in and day out, unless you're like me and you have Sirius satellite, is 88 megahertz to 107.9 or 108. Each of those radio stations is 15 kilohertz. So they take 88.13579 and they drop a 15K circuit in there. So on an FM radio dial, if I was in New York City, I could have exactly 100 radio stations. No, I could have less, but no more than that because we do radio stations every odd frequency. So we're doing the same thing, and the same rules apply to FM radio. So I live out here in West Texas. We're very, very flat. There's not a lot of hills out here. So I can start driving 60 miles away. I can get almost down to Abilene, which is about 90 miles, but about 60 miles away, if I'm listening to the FM radio dial, all of a sudden around the 60, 55 mile mark or so, something in there, I'm going to start picking up the Rice Krispie triplets in my music. I'm going to be singing along, probably singing the wrong words, or at least the words that I know it as. And I'm going to, but I'm going to start getting noise and distortion because my signal has attenuated. My signal's attenuating from the radio tower. It can't go forever. And about 70 or 75 miles, I'm looking for a new radio station. Is that pretty close to what you all do? Maybe not. Maybe if you're in a mountain area or something like that, you're switching radio stations more frequency. But you get the point, correct? And the same thing is going to happen in the DSL world. The longer that cable pair, the more that signal is going to attenuate or lose power. Now, have an X and Y axis here. So if I look on the far left, my 0 to 15 bits on my X axis, it says I can get 15 symbols, and we're going to call them symbols. You can call them bits if you want, but there's a lot of bits in each one of those symbols. And on the Y axis down there, it goes out to 1.1 out there. So this is an ADSL circuit. If it was 2.2 or something like that. But you can see that I will get more bits in the lower frequency modems than I will in the higher frequency modems. So when we start looking at the graphs and things, you're going to hear me, you're going to see the staircase. I'm going to say you're going to see a staircase on here where your bits are going to start dropping down in those higher frequencies. Now, let me ask you this question, and you'll probably know this TV character. How many of y'all have ever gone out on a DSL line and your Leroy Jethro Gibbs gut check says, I am way too far out here for this thing to work? Anybody?
We've done it here in Ferndale.
Yeah, you get that gut check that says you're too far away. Did you know that there's a graph that's going to show you that you're too far away, or that you're not far at all, or hey, you're getting close to the end of the road?
No, I didn't know about that graph.
Yep. So we're going to talk a lot about the graphs. So now when I get out here, I've got my transmit power. Okay, so I'm shooting this thing like a bullet coming out of a gun, except that bullet is going to lose speed over distance, And so I start out with this. Well, that signal is going to attenuate and lose power. Now, I have something called signal to noise ratio. How much signal do I have versus how much noise? Very close up, I've got a lot of signal to beat any noise that's out there. But as I start to go out there, there's my SNR. The farther I move out there, my noise floor is going to start to come up. My signal to noise margin is going to start to rise. And sooner or later, this stuff is going to start impacting. The noise that's in there is going to start impacting and coming up into my data. So my SNR, chances are your D-slams are probably set to a 6 SNR. You can't go below that. The higher the number, the better. It means I have more signal than I do noise. But just like your FM radio station, when I get out there too far, there's not enough signal to block the noise coming up. And that's when you start hearing all the noise and static and stuff. Does that make sense? Okay. How many of y'all are used to seeing a screen that looks like this for doing your DSL, looking at your actual rates, your show times, and all those good things?
That's the #1 screen we use.
Okay.
Yeah.
So that and your error screen, I'll just jump down to this page and I'll come back. You have these two screens. On the ONX, it's on one screen. If I was to say 0 to 100%, how much do these two screens mean that your line is good? Is that what you're relying on, those two screens?
Most of the time.
Okay. So it's only about 25% to me. So this just tells me, okay, 25%, I think that this is good, or I know it's going to be bad. Where am I pulling my other 75% from? The DSL graphs. So the DSL graphs are more important than this. This is giving me some good information, but if I don't want repeats, I'm going to be looking at my graphs big time. Does that make sense so far, even though we haven't gotten into the graphs yet? But we will be. Does that make sense?
Why wouldn't you just the pair?
Pardon me?
Wouldn't you check the pair instead of relying on the graph first?
Oh yeah, I've already done my good pair check. But there's things that can be out there. If you don't do your good pair check, #1, you don't know if you have AM radio interferers. You don't know if you have bonding grounding interferers. You don't know if there's a bridge tap out there. If you have, if you're only running the multimeter, you're totally blind to all these other anomalies.
I see.
So first thing I'm going to bring up on the far right-hand side, it says this is ADSL 2+. If it's ADSL, there's one of 6 or 7 flavors of ADSL that it'll pop up there. If it's VDSL, it's going to tell you you're an 8A or a 17A or an 8D profile. There's A, B, C, and D profiles. But we only use 17A here in the US. And 8 could be either 8 or D is what I typically see. Just tells me what I got. Now, your actual rate, your max, your capacity, and your noise are the ones that you key off of. Pay zero attention to line attenuation and signal attenuation. Neither one of them is going to buy you anything to tell you what is going on in that cable pair. If you're looking at it, chances are you don't know what you're looking at. I don't mean to say that rudely, but I'm being honest. The only way line and signal attenuation works is the only company I've ever seen it work for is Thunder Bay, Canada. Because all Thunder Bay, Canada has is 22 gauge cable. That's it. They don't have any 22, 24, 26, or excuse me, any 19 or anything. They're all 22 gauge cable. They're up in the middle of nowhere, Canada. And so if you only had one cable gauge, then you can figure out what your line and signal attenuation is supposed to be. If you've got multiple cable gauges, all bets are off. Now, your actual rate, your max rate, your capacity and noise margin, I may only be able to use one of these values, and that will be the actual rate, depending on how your D-slam is set. Now up top there, you see the estimated loop length that says less than 1,000 feet. That estimated loop length can be very accurate, or it could literally be miles and miles with an S off. So the estimated loop length is calculated on 26 gauge or 0.4 millimeter cable. That is the IEEE standard on how DSLAMs calculate this. It doesn't know what 24 gauge is, 22 or 19. So if you had all 26 gauge cable, your estimated loop length is going to be pretty accurate. If you have a mix of 22 and 24, you might be off 15 to 20 percentage points. If you have 19 or 22 gauge cable, you'll be off by miles. So where my ranch is, before I got fiber here, I was 22,000 feet from the DSLAM. I'm on straight 19 gauge cable. We did the opens measurement as 22,300 feet out there. And when I did my estimated loop length, it said 8.7 kilofeet. Missed it by 3 miles. So it doesn't know what 19 gauge cable is. So you have to, sometimes you got to understand what you're working with on that estimated loop length. Now, if your DSLAM is set properly, the only thing I can really go on is your actual rate. So there's an option in your DSLAM. I do not know if it's set or not. It should be set. Chances are, if it's not, people haven't set it because they don't understand what it is. It's called power back off, PBO. Does anybody know if you have PBO turned on in your DSLAMs?
I don't believe ours is, no.
The real quick way to tell is right now I'm at the cross box. When I made this measurement many years ago, I just haven't updated my presentation because I mainly do fiber stuff. One of these days, I'm going to have to go out in the field and get some good screen captures on the ONX and just update this. I am 50 feet away from the DSLAM. I got a 50-foot stub. What do you think about these readings for 50 feet? If you were out in the field and you were at the cross box and you saw this, what would you think? Look at your capacity and noise margins. Could you live with 86 and 88% capacity at 50 feet?
No, not at 50 feet.
This is what you want to see. So this means I have power back off turned on. So what power back off is, let's say that to a normal DSLAM without power back off, it is transmitting at full power. Now, there's some pros and cons to full power. Full power is going to reach out as far as it can go on that cable pair based on gauge and distance. However, when I put full power on, I am going to start flooding your 25 pair cable with egress, internal noise. So the internal noise coming instead of ingress noise coming from the outside world. So you may only be able to get 14 or 15 or 16 users in that 25 pair binder, instead of 18 to maybe 20 if you ran power back off. So let's say we're in a conference room and the conference room's 50 feet long, mimicking my 50-foot cable there. And I don't turn power back off on. So I'm going to transmit at full power, which means I am going to scream and holler at you at the top of my lungs to carry on a conversation. What are you all going to do? You're going to put your attenuators in your ears, your fingers, to block me from screaming at you, correct? But that's what's happening. You have all these ports screaming out maximum power. So what power back off does is power back off figures out how far away you are, and it dials the transmit down so we can have a normal conversation like I'd have in the conference room. Does that make sense? So it doesn't need full power to go 50 feet. It needs very low transmit power. But when I lower the transmit power, your capacity is going to go up, your noise margin is going to go down, and that's perfectly fine. Now, let's say I unplug from there. I drive out 4,000 feet on this ADSL 2+ circuit, and all of a sudden I get a new sync, and it now tells me, hey, your capacity is 78% and your noise margin's 14. Well, that looks a whole lot better, right? But it had to turn the transmit power up to get out there that 4,000 feet. Does this make sense? So I have talked to the AdTran engineers. I have talked to Nokia. I have talked to Zone. I have talked to Calyx engineers. And I've talked to John Rice, my former senior software engineer that sat on the ITU forum for DSL. And I said, can any of you give me one reason why not to turn power back off on? And you know what their answer is? No, everybody should be turning it on, but service providers aren't doing it because they don't understand the benefits to it. So if you're getting really cruddy readings like this at the D-Slam, just smile and say yes because power back off is turned on. If you're getting something like 60% capacity and an 18 for noise, that means power back off is turned off. Does that make sense?
It makes sense, but what can we do about it?
If you want, you can get your D-Slam folks to give me a call, and I'll be glad to, talk with them and explain these things. I know a lot about D-Slams. I know enough to be really dumb and super dangerous, but I'm not an expert. But my question, my thing is, what I'll tell them is, hey, go back to Adtran, go back to Calyx, or whoever's making your D-Slam, and say, what are the optimal settings that we should be setting for? Those guys and gals know exactly what the optimal settings for their D-Slams are, and they're going to turn on a whole bunch of stuff that you're not turning on. So what I tell people right now is Jeff Passmore, who retired from us about 5 years ago. Jeff came out, and when Broadcom came out with the 63168 chipset and all these new features that you can do in the D-Slam, he said this stuff is getting pretty close to working on barbed wire fence with this new chipset, because it has so many cool features that if you're not turning them on, you're not getting the benefits out of them. Now let's talk about errors. All right, where'd my mouse go now? And why are you not working? Okay, there we go. Let's talk about errors. There's two types of errors, FECs and CRCs. There's three ways to look at those two types of errors. If you get one CRC or multiple CRCs, your line is, there's something wrong on your cable pair. I don't care how hard you argue. I don't care if there's one CRC. Theoretically, CRCs should not happen. If they're happening, there's a serious problem on your cable pairs. FECs, I don't care about periodic FECs. The single largest FEC hit in theory I could have would be 60,000 bits. If I got a hit of 60,000 bits with no CRCs and I go minutes between those events, that's cool. If your FECs are rolling like the national debt clock, they're just counting, you are guaranteed a repeat. You are guaranteed that customer's modem resetting depending on multiple times a day or a lot of times a day based on how fast those errors are rolling. So periodic FECs, they're perfectly fine. They're going to happen. If your FECs are rolling or you have CRCs or you have both, you have a line problem on your cable pair. Does that make sense so far?
Yeah.
You have two options in your D-Slam. One is called fast, one is called interleave. When you run this, what happens when you run interleave? Interleave makes sure that your line is pretty daggone bulletproof from taking FEC or taking CRC errors. FECs are going to happen. They're going to get fixed. Fast, depending on how your fast settings are, if you set your fast settings real low, you could take away up to 80% of your forward error correction and just be getting CRCs. So fast, there's a lot of variables that go into setting in that D-Slam on how you want to be able to set fast. But in the interleave world, anybody that was doing IPTV, you had to do interleaving. There was no way it was going to work on fast. So when you transmit your data, that's that top line of color-coded red and green and blues. You have your ATM data, and then what happens is the system makes a backup copy that it transmits. So I'm going to pick on Richard because he's the only name I see on my screen right here. Richard, last name is Claims or something close to that? Clemis, thank you. I'm going to pick on you. You're my UPS driver. So they load 100 boxes in the back of your UPS truck, and they're labeled 1 to 100. and I'm your UPS driver number 2, and I'm going to set about 30 seconds behind you. Now, in the real world, this would be done in millionths of a second, but for drivers, we're going to be 30 seconds. So I have the exact same packages, and you're driving down the road, and there's a massive pothole across the entire road, and you hit that pothole, and all of a sudden your back door swings open and 3 packages fall out, and your back door slams shut, and you don't realize you just lost those 3 packages. So you lost package 48, 52, and 88, but you don't know this. You drive to the office building, you unload 97 boxes, and you go, ruh-roh, Rorge, I'm missing 3 packages. Now I'm driving right behind you 30 seconds. I hit that same pothole. Hopefully my door doesn't bust open and I lose packages, but maybe I did. Maybe my door maybe we hit really good and my door busted open and I dropped a couple packages out. So I get to the other side and Richard, you say, oh, thank goodness you're here. I need packages 48, 52, and 88. And I pull those out of back of my truck and I said, there they are. So we call those FEC errors. I fixed the errors through the backup frames. Does that make sense?
Yeah, forward error corrections.
Yep, forward error correction. Now, let's say that pothole was big enough that all of a sudden I dropped packets 48 and 52 as well, and a whole bunch of other packets. But you needed those 3 packets, so now I was able to give you packet 88. But we don't have a 48 or a 52, that's going to go down as an FEC error because I couldn't get it from a backup. Does that make sense?
So if it can't fix it, it automatically put a forward error correction in.
Nope. If it can't fix it, it's a CRC error.
Oh.
If it fixes it, it's a forward error correction.
Yeah, because that error correction could be coming on the next truck.
Yeah, it's the forward error corrections coming out of the interleaf packet, or out of a fast algorithm. And again,
so
depending on how you
when the third truck shows up, it might have the boxes you guys need.
There is no third truck. There's only 2.
There's no third.
There's the original and the backup frame. You don't get a third shot at this. So that big pothole that's across the road, that means anytime you transmit data, it's going to hit that pothole just like it's going to hit a bridge tap or something else, or a high resistance or something else on that cable pair. It's going to cause those errors to happen, correct? Again, I don't care about periodic FEC errors. But if my FEC errors are rolling like the national debt clock, you have buffers in your DSLAMs and you have buffers in your DSL modems. And sooner or later, you're going to overflow those buffers. And what's going to happen is as soon as that buffer overflows, you're going to get a loss of signal, loss of frame, loss of margin alarm, and your modem's going to reset. Make sense? Okay. So let's look at our graphs. We're going to start to look at our graphs here. So now I'm looking at the graphs, and if you look down here in the bottom left, this is if you look there, you'll see that, hey, if I go across the top of the page, going across the y-axis there, it says 100, 200, 300, 400. What is the next logical line out there? What would that be labeled as? Anybody? 500. But it didn't stop at 500. It went a little bit past that. So now the graphs are showing you all of your DSL submodems. In this case, I'm looking at all 512 submodems. Now, if you look at the far left, it looks like something like an Empire State Building. Anybody know what the Empire State Building is in DSL, or that high rise?
Or upstream.
Upstream.
That's your upstream data. That's all your upstream data. Everything else to the right of that is your what?
Downstream.
Downstream. Okay, starting at around tone 300, can you see the staircase? Remember I told you there's going to be a staircase? Can you see the staircase? And it's not a perfectly symmetrical staircase. That just means that those higher frequencies above tone 300 can't handle as much data as the closer frequencies. Now, I can put as many as 15 bits or 15 symbols into each DSL submodem. So let's pick on tone 100 here. Tone 100 has a white grid line through it, and Tone 100 is getting all 15 symbols. What does that mean? For each symbol, there's 4,000 bits of data. Okay, so 15 times 4,000, that means Tone 100 is transmitting 60,000 bits of data per second. Now, find about Tone 385. Anybody want to take a stab at what grid line 385 would be on? Anybody? Just a guess? 8. So 8 times 4,000. So Tone 385 is doing 32,000 bits of data per second. So if you were to take your cursor and go across and label all those submodems and count how many tones there are, multiply it by 4,000, you would get your downstream data rate or your upstream data rate if you did the upstreams. Does that make sense? Now, if you look at that little notch out between 3 and 400, around 375 to 390-ish or something like that, look at the SNR graph on the other side. Do you see that same notch out?
Yeah.
Yeah. So your signal to noise ratio graph is going to parallel your bits per tone graph. So just like an FM radio dial, there's a little bit of noise and distortion in there in those frequencies. But hey, I'm still getting data. I'm still getting 32,000 bits of data in there, correct? So no harm, no foul, because I have this thing called forward and reverse bit swapping, where I can shuffle my data around between different submodems. Some submodems will say, hey, I've got capacity, give me your data, I'll send it over here. Now, these two slides came out of Lincoln, Nebraska, back around 2005 or so. But you can see the Empire State Building there. Again, I forgot what was that again?
Upload channel.
Upload. And then you can see all the download stuff there, and you can see the big staircase going down there. But look at the SNR graph right past 1095. You can see 3 mountain valleys. And they're impacting that bits per tone graph, aren't they? Now, the little two to the left are only impacting one submodem each. It's just a straight line down. But the bigger one on the left is affecting multiple submodems. Now, the kicker to this was we weren't even taking FEC errors because these were minimal. Had they gone down to the 0 mark or been wide spaced, knocking out tones altogether, then that would have been service affecting. So can you kind of see how your bits per tone and SNR graph can start to show you some stuff? Now the coup de grace. Go to the quiet line noise graph on the right. This line should be relatively straight across there, but I see 3 mountain peaks. Are those 3 mountain peaks at the exact same location as those 3 mountain valleys on the SNR? Yep. Now, what I tell people to do is draw a set of goalposts between 547 in this case and the end of the cable pair and focus right in between there, because what you're looking at is you're looking at 3 AM radio interferers. Okay, so those are so when you're looking at that spectral analyzer between 500 thereabouts and 1700, that's the AM radio frequency band. How do we keep AM radio out of your plant? Bonding, grounding, shield. So had you run your good pair check, your G filter would have lit up like a Christmas tree. That would have been a big red X. I always call it checks and balances. Good pair check says, hey, you got, the check part says, hey, looks like you've got bonding, grounding, shield issues. This is your balance. Yep, you do have bonding, grounding, shield issues. We just happen to be far enough away from those AM radio stations that it really wasn't service affecting. Does that make sense? You have another graph called H-log. H-log is your distance graph. It's not distance in feet, it's distance in attenuation. In this case, I have a red line and a blue line. That V that you see on the red line, that's a bridge tap. So pair 2 on here has a bridge tap on it. The blue line is just straight. There's no bridge tap. What I want to see is I want to see a nice straight line from left to right. Now, that blue line, red line, we'll just concentrate on the blue line right now, It doesn't even quite make it down halfway down the page if we look on the far right. It's almost, we're about one green slash from being halfway. So if somebody says, is this a long cable pair? I said, this is a very short cable pair. My line's not attenuating very much. Now, what happens if I had this? What happened to the pair?
Got cleaned up.
It got a little longer because my line's tilting more down to the right. So the more this thing drops to the right, the longer the cable pair is. How about if I had this?
Super long.
I'm getting very close to the point of no return of being able to handle my actual rate. But you still see there's a little bit of daylight there on between that and the bottom, correct? Now, what happens if I had this?
You have to tell them to either change their speed or move their house closer to the D-slam.
The D-slam should automatically do the speed unless somebody's gone in and done something really silly and turns seamless rate. There's an option in your D-slam. It is, and everybody's D-slam, it is defaulted on. It's called seamless rate adaptation. And seamless rate adaptation will drop those speeds automatically based on the line conditions that it sees. What happens if you see this?
They're out of service.
Nope, they are way too far. So remember I told you, you do a ton of RDSL? When I told about all those different types of DSL services, I say you do a ton of RDSL, but nobody's ever told you that. That's called rate adaptive DSL. So let's say I'm a 50 meg VDSL circuit right here. I'm getting 50 megs. I hit this, my D-slam's now changing me to 48 megs. I hit this and it's now giving me 40 megs. So the farther I start going back to the left, seamless rate adaptation is not going to have all those submodems to work with. My data rates are going to start to get lower. Does that make sense?
But as you lower their speed, that line should go back up towards the right and flatten. No.
It just means that if I'm lowering the speeds, I can only work with what I have here based on the distance.
So it has nothing to do with the provision speed. It's just giving you the max attainable.
Yeah, it's just saying I can't achieve 50 megs. I can only achieve this based on the cable gauge and the length of this pair and all the line conditions that are out there.
Gotcha. Okay.
Okay. Now, if you were at a cross box and the D-slam was right next to you, about 10 feet away with a 50 or 100-foot cable across, to it, what would that line look like at 50 or 100 feet?
Should be flat.
Yeah, it should look just like that, correct?
Yes.
Because I don't have any measurable attenuation at 50 or 100 feet. I just know the farther I move out from the D-slam, this is what's going to start to happen until I get down here. So there's, so if you had that thing, if your Leroy Jethro Gibbs gut check says, Jeff, I think I'm way too far out there. How are you going to prove it to yourself? Go to the H-log graph, because the H-log graph is going to be your distance graph. Now, this graph to the right here, this quiet line noise graph, this came from Frontier in, I think, Connecticut or upstate New York or someplace up in the Northeast, the old AT&T area that Frontier had picked up. And one of the staff guys called me many years ago and said, hey, Jeff, we have been 2 weeks working in this cable, and we don't have one working customer, not a one. And I tell people, like, if you really get stuck, you're going to have to send me your graphs. So they emailed me the graphs, and I said, well, heck, there's your problem right there. And they're like, oh, come on, dude, what are you looking at? I said, go to your quiet line noise graph. I said, my gosh, how many ADSL 2+ customers do you have in that binder? And they said, I don't know. I said, well, somebody go figure it out real quick. And they came back and they told me they had 22 ADSL 2+ customers, and they were putting in this VDSL circuit. And they said, how do you know? And I said, that line should be straight across the page. You see where it says 1650? You see where the line goes straight? If they move that purple cursor, that pink cursor out to that line straight, it would have been at 2.2 megahertz. It would have been right at the ADSL 2+ end of the ADSL 2+ spectrum. What I'm looking at here is all the egress or the crosstalk from all those ADSL 2+ customers being in that 25 pair binder. Do you see where your graphs can come in? After 2 weeks, I said, you have fixed and found any copper problems that were out there. I'm not worried about your cable pairs. You've rebonded, regrounded, you've done everything. You have an internal noise issue. And the only way to get rid of this is you're going to have to get 4 or 5 people out of that binder group. And that's what they ended up doing. Do you see where your graphs can help you, where your normal cable testing isn't going to find issues? Okay. So if we look at this graph right here, this is the VDSL graph. What would you say about the distance on this? Anybody?
It's fairly far.
Fairly far. Am I getting close to the point of no return?
Yeah.
But do I still have a little bit of daylight there?
A little bit.
Yep. So I should be good. Now, this one was a very short cable pair. It wasn't even 1,000 feet. But we had a high resistance open on it. A series fault is what it's called. You all call them high opens and things like that. So when there's a problem, it's going to hit that problem. It's going to automatically start dropping down. Now, bridge taps, remember that first one I showed you had that little bitty tight V? They don't typically look like that. Bridge taps are done by bounces. So if you look at the top screen there, there's a bridge tap there. It's got 1 bounce. You may have 1 bounce. You may have 2 bounces. You may have 10 bounces. Every bounce is not a bridge tap. The more bounces you have, it just means that bridge tap is closer to your DSL modem. And it's affecting multiple, the closer you are to that bridge tap, the more it's going to affect that line. The farther out it is away from it, the less it's going to affect the line. So there's a before and after. Okay, let's do some troubles. So this first trouble, 9 truck rolls. This was out in Lincoln, Nebraska with Windstream. And I happened to be out there on business. And Kevin Fish is one of the national staff guys for Windstream. He says, hey, I got a couple of troubles. Can you go out on this afternoon after our meetings? I said, sure. So I asked the technicians, this was before the ONX. I said, did you run the good pair check on the HST 3000? Oh yeah, both pairs tested good. Okay, there's the graphs right there. And I said, you did not run the good pair check at all. There's no way. So the first graph shows pair 1 and pair 2. Pair 1 is in blue, pair 2 is in red. And then the other 2 graphs show just pair 1 by itself and pair 2 by itself. I don't have a staircase there. I have missing stairs. And if you look at the SNR graph, you can see where those missing stairs go all the way down to the noise, all the way down to the 0, and there's wide gaps. Does everybody see that? Can you see why this line's having problems?
Yeah.
Yeah. So then we run the good pair check. Oops, sorry. We go to the H-log graph. Sorry. So what do you think about the H-log graph? Do we still have some distance there?
Yeah.
Yep. Now look at the quiet line noise graph. You see those 3 mountain peaks between the 0.5 and 1.6? What are those?
The AM?
AM radios. So then we ran the good pair check, which they should have done the first time. And what do we see? The G filters light up. So I said, had you run the good, and 3 of the guys that went out twice were the 3 chronic guys out of the 9 truck rolls. All they had to do is run this good pair check the first time. They would have known they had a bonding grounding shield issue. Can you see if they'd run that and saw that. That's what they were going to see, those AM rate. That's the check and balance I was talking about. Does that make sense?
Is there any way to measure where you might?
Nope.
You just got to do the whole run.
Yeah, so Dynatel came out with, and I've got the algorithm buried somewhere, someplace, but they came out where you could put your test leads onto one of the conductors and then put your test lead on a shield, put the other lead on a shield and run a TDR, but you had to run it from both directions. And then you run this, it's a real simple algebra equation. And it would put you about 300 or 400 feet away from where the actual shield, ground, or bond was open.
Well, that's only 2 sections, so that's not bad. That's not a bad test.
Yeah, depending on how far the sections are and things like that.
Yeah. Mm-hmm.
So
it's pretty cool.
Yep. Okay. So this one came from, let's see, what am I doing here? Okay, that's that. Okay. So this one came from AT&T in McKinney, Texas, where one of my boys was acting supervisor. And he says, Dad, I got 2 new people out there and they don't know what they're doing. And they're having problems on this bonded circuit. It was supposed to be a 50 meg up and a 6 meg down circuit. And I'm like, okay, let's see what's going on here. So it tells up top, it's a 17A VDSL profile. Okay, we get that. But if you look at down the bottom left, pair 1 is running clean. Pair 2 is running awful. It's got 62 FEC errors and 1,617 CRCs, and we haven't even got to the minute mark yet to figure out how many per minute you're getting or what's your average per minute. So if you look at top, can anybody look at the top right one and tell me what the physical cable pair problem is? Are you able to pick it up out of those results in the top right?
You got a noise issue somewhere.
Okay. But what's the physical cable pair problem? It's right there on the end of your nose. You're just not looking there.
Bridge tap.
Thank you. Why do you say there's a bridge tap? You're correct, by the way.
I say it off of the line attenuation.
Okay, but if you look at the estimated loop lengths, right below where it says showtime, pair 1 is 1.8 kilofeet, pair 2 is 2.3 kilofeet. Why would pair 2 be longer?
That's the
bridge
tap.
Yeah. So I've got a bridge tap on there. Now, if we go down and look at the bits per tone graph, if you look at the red one goes down and bounces back up, correct? It has that telltale V, where the blue one's just kind of like the staircase there. Let's look at this easier. Okay, there's the blue one. It's got a beautiful little staircase to it, doesn't it? And look at the red top right. You can actually see in the bits per tone where it goes up. Now, back when we took this picture, the Nokia D-slams did not report the upstream data. So that's why you see the blank in between those two. So VDSL starts with a big downstream, then an upstream, then a downstream, then an upstream, then a downstream. So there's up to 3 downstreams, 2 upstreams. So if I was to take a blue marker and draw a straight line between those 2 openings, would you see any bridge tap on pair 1?
No.
No. But if I took a red marker, how many bounces would you see on the red one?
2.
2. You definitely got a bounce there, but it looks like the transition's already going down. The transition from right above 13.2 is coming back up again. So yeah, I would have 2 bounces in there. So there's a bridge tap there. So I said, knucklehead, you didn't run your good pair check, and AT&T, it's called the true test. It would have showed you had a bridge tap and how far, and the TDR would have showed you how far out it was. So we shot the TDR, went over. It was a second drop that was down a really long driveway that was left as the second pair that was left in. So we cut that off at the pedestal, and life was good. And we went back out there and ran everything, and everything tested good. Does that make sense? This next trouble was up in St. Louis, Missouri. It's one of the smartest AT&T outside plant technicians I've known. His name is Gary Myers. I think he's since retired. But I go walking into his boss's office, and he looks at me and says, I need you today. I said, what did I do? He says, I have a chronic trouble, and your stupid test that's telling me I have a bridge tap on it, and there is no bridge tap, and I cannot figure out what's going on. I said, all right, I'll give you a call. So I got his number. When I was done with my meetings, I hooked up with him and I said, all right, what do we got here? So we go over here and we're not running any CRCs, but I'm running 1,640 on average FEC errors per minute. That means this thing's rolling like the national debt clock, correct? Which means his modem's going to, when I overflow the modem buffers and the DSLAM buffers, it's going to reset. Okay. So I look at my capacity. Capacity is not bad. Noise margins are real good, except on the downstream, but I'm running these errors. So we look at the graphs. And as soon as I see the graphs, I'm like, Gary, you have a bridge tap out there. He said, Jeff, I do not have a bridge tap. There are 7 homes. They're all on half-acre lots. And he says, the farthest cable I have out here is about 375 feet to the house. So we looked at the H-log graph and I said, Gary, you have a bridge tap on there and it's very close. You see all those bounces right there on the top right H-log? The more bounces, the closer the bridge tap is to you. So we shot the auto ID TDR and it says you have a bridge tap at 140 feet on a 290-foot section. He says, Jeff, there are no bridge taps in these facilities. I said, Gary, this is not rocket science. It's either in that pedestal or that pedestal. Which one's headed back towards the DSLAM? So we picked the one going there. We open it up, and what did we find? The neighbor's orange-white drop from his old second line was still connected. He was like, son of a gun. I didn't even think of a left-in drop. But he spent the previous day out there going through everything, trying to figure out what it was. Had he just shot the simple bridge tap and gone to one of those pedestals, he would have been able to find it. Does that make sense?
Yes. So have we been trained correctly when we learned that a short bridge tap close to the house is worse than a long bridge tap further away from the house?
I hope you have, but at least I've told you today.
That's the rule of thumb, though, usually, right?
Yep.
A longer bridge tap further away from the house won't nearly affect the service as a short bridge tap closer to the house.
Yep.
Okay. All right, then we're correct.
Yeah, the short ones are gonna be really service affecting because you're whacking out all those tones. I mean, you're impacting all these tones that you've got there. Whereas the one bridge tap might just impact the back end of it, the front end, or something in the middle. Maybe it doesn't go down all the way to the 0 line, and we're able to do some rate adapting and some bit swapping in there to fix that. Okay, this next one we're back up in Lincoln, Nebraska, third truck roll. This one was really interesting. Look at the estimated loop length. Pair 1 is 4.5 kilofeet. Pair 2 is 3.5. So I've got a 600-foot difference on pair 2, but pair 2 is the one I got trouble on. Anybody want to take a gander at what's going on?
One side open, possibly?
Open.
No, I wouldn't. Well, one side open, no. But I'm getting a lot of FECs and CRCs, correct? So we look at this and it's like, wow, you got a ton of noise in there. Because if you look at the SNR graph, you can see all the hits it's taken. The H-log graph doesn't look too bad, but what do you see on the quiet line noise graph?
AM radio.
AM radio, but there's more problems. So unfortunately for these knuckleheads, their area manager and their district manager came for a ride with us to see what was going on. And so I said, did you run the good pair check? Oh yeah, it came up clean. As soon as I ran the good pair check, I'm like, guys, how did you miss a 3 meg ring ground? I don't know how you missed that. Your G filter and your G and F filter lit up. Tells me that you have bonding and grounding issues. I have a ground resistance issue and I have a resistive balance issue because of those that wide swing up there on the leakage side of life. And I said, guys, you got a bonding grounding issue. We got to fix, so we got to do an RFL to figure out where that ring ground is at 3 megs. So we shot an RFL. It sent us to a pedestal. We lifted up, opened the pedestal, and you see the orange-white hooked up and the white-blue hooked up. That one right there in between there, you see all that green corrosion? That was their ring ground issue. That corrosion was through and through. And you can see it on there. And so there was an auto zone that I could see about diagonally from where we were, about a mile away. I could just see the auto. And so I said, hey, this technician, go to AutoZone and buy me some light bulb grease. He says, light bulb grease, what for? And I says, because I need some light bulbs that need greasing. And Kevin Fish says, get on your way, go buy the man some light bulb grease. So I said, somebody go get their wire brush. So they took all the lugs off of these things, cleaned off all that corrosion and everything. And then before we put the lugs back on, the kid came back with the light bulb grease. I said, now put it all on the ring sides and then put the screws back on and put the light bulb grease back on those and hook everybody back up. And they said, why not the tip side? Anybody want to take a guess why we didn't do the tip side? Only the ring side? Tip side is ground, ring side's your battery. So the ring side is drawing drawing all that, and it's getting that, it got wet or something and started corroding in there. This last trouble, this was in Hawaii, and this is when the ONX first came out. So we didn't have the good pair check. We had the one check copper. So if we look at the one check copper measurement, it's 15.6 kilofeet on the opens pair. I don't know if you can actually read it on your screen. Can you see what the actual estimated loop length is on the second screenshot there that has showtime?
5.2 kilofeet.
Okay, so I've got a 2 mile difference between the actual open distance and the estimated loop length. Anybody want to take a guess at what's going on that cable? What did I say would make your estimated loop length be off by miles?
A modem or something?
19 or 22 gauge copper. So I've been covering Hawaii for 27 years. So when this happened, I got all excited. I said, we're headed to the North Shore. We're either going to the coffee plantation or we're going to Dole Pineapple. How do you know that? I says, because I've been out here I come out here 2 or 3 times a year. I used to. Now I only get to come out once a year. But anyways, we were going to Dole Pineapple. So we looked at this thing, and if we look at the FECs on the third line, when they took this screenshot, it was 28 and 1 CRC. Okay, so we got some problems here. Now let's look at the bits per tone graph. Can everybody see the Empire State Building there?
Yeah.
And then you see your downstream, but your downstream doesn't make it out to the 2.2 megahertz. It's only making it out about 1.6, 1.7. So I've got a huge distance issue. I'm too far out because I'm not using that last inch of modem tones, correct?
Yeah.
So now, if we look at the H-log graph, that's your distance graph, but you could still do it on the quiet line, on the other one. So I can see that, hey, it's dropping down. It's dropping off about 1.6, 1.7. But then look at the SNR graph. You see those 3 big hits right there? So I got something hitting the line. Now go to the quiet line noise graph, and what do you see between 500 and 2 megahertz?
Bunch of spikes.
Yeah, what are those mountain peaks supposed to be? What causes mountain peaks?
A short?
Nope. AM radio.
Radio.
So look at all those AM radio stations. Now, Dole Pineapple is on the North Shore. All of the AM towers are on the North Shore. So those AMs are they're pretty steep, aren't they? I said, all right, guys, well, we're not going to get, I meant to tell you, oops, let me go up. I meant to tell you this was supposed to be a 12 meg downstream and a 1.3 on the upstream. We're getting the upstream right. We're only getting 8.2 on the downstream because it rate adapted down. I said, guys, we're not going to get them any higher than 8.2 or 8.3, whatever that was on the other side. But we can clean up their errors by fixing the bonding and ground stuff. Dole and the coffee plantation have since had fiber put into them. So does this make sense, and is this helpful?
I just have a question about the QLN.
So when you're talking about the AM radio, is it always that big spike, or will it also be those dots like we've seen previously in other
Yeah, it's
slides?
just it depends on the strength of that AM. If it's way far away, it's not going to have a very tall mountain peak, but you will see a mountain type peak if there's AM radio in there. The closer that AM radio is, and the more power it's getting into your cable, the higher that peak's going to be.
And if you're getting those AM strikes, then you need to go check your grounds. Bonding,
grounding, shields, all three. And make sure they're properly torqued. So I'm going to share this last slide since we have a few minutes, and then I'll open it up for Q&A. I want you to understand how DSL works. And DSL in its simplest premise is very simple. It is also extremely, the sensitivity of these receivers is beyond anything. So all modems since 1968, when the first modem came out, works on a $25 college word called quadrature amplitude modulation, or QAM. Anybody ever heard that term before? And what QAM does is it takes the analog waveform and it shifts it 90 degrees to the right or 90 degrees to the left. It also shifts the power up and down. So if we look at the top left, we see this QAM, it's 4 QAM or QAM 4. And we've got a crosshair there. We've got 4 quadrants in that. Everybody see those 4 quadrants? They've got some numbers there. We'll talk about those numbers in just a second. So look over to the far right, the top right, we see the very top one is a 90-degree phase shift to the right. So we've shifted the analog wave sign 90 degrees to the right. The next one down, we shifted it 90 degrees to the left. The third one down there, we shifted it 180 degrees. So we flipped it over on itself. All these degree changes are what's going to determine what your bits are. And then the fourth one down there, I just drew a dotted line down there and showed you all 4 quadrants. Does that kind of make sense how we're shifting these wave signals? Now let's go back to the top left one, the 4 QAM. 4 QAM's real simple. I can only have 2 bit combinations, a 1-1, a 0-0, a 0-1, and a 1-0. So what I do is what the system does is it puts those two binary combinations into each of the 4 quadrants. So Richard, if I was to send you a 1-1 pulse, I'm going to shift that wave sign so when it arrives to your receiver, which of the 4 quadrants is it going to be in? I'm picking on you again. I apologize.
Is it the bottom left quadrant?
Bottom left. So if your receiver picked that up in the bottom left, you know that you have to send into the customer's equipment a 1-1. If I send it to you in the top right, what's your bit combination?
It could be 0010 or 0000s.
No, if it's the top right, it's just going to be 00.
Okay.
Yeah, we're on the very top one. We're just doing QAM 4. We haven't done QAM 16 yet.
Oh, okay. I was looking at QAM 16.
Yep. No, we're good. So this is pretty simple when you look at his QAM 4, correct? If it shows up in any of these 4 quadrants, now let's make this a little bit more complex. This is QAM 16 with 4-bit combinations. So now I have four combinations in each of the 4 quadrants. I added a little bit of animation there to show you how this changes. Now, how sensitive do you think your receiver has to be able to pick up the correct of these 4 quadrants? It's got to be pretty darn sensitive here. But I'm going to drop down to this next page. That's only QAM 16. With 15 bits, we do QAM 32,768. That means in each of those 4 quadrants, let me go back to the 4 quadrants here, there are 8,192 different points in those 4 quadrants right there. Now, how sensitive do you think your receiver has to be?
Super sensitive.
No, we're beyond. It's off the spectrum how sensitive it is. If you were to look at my computer screen, but you can't really see, there's a whole little dots or the pixelations that I can see. I bet you if I drew a box in there, there aren't 8,192 little dots on that in any of those 4 quadrants. So for that thing to be QAM 32,007 to get 15 bits, like I showed you that one, Tone 100 had 15 bits in there. That receiver sensitivity is incredible. When we go to G.fast, we now do 16 bits, and there's over 65,000 or over 16,000 in those quadrants. But my distance limitation is about 300 feet. I don't have a very far distance limitation on that. But this is why you're out there qualifying these cable pairs and making sure that you're as clean as can be, because when these receivers look to get this sense, to figure out what quadrant it is and which one of those things is, it's not hard to get off by a nibble of a degree and pick the wrong bit combination. And then hopefully we figured it out on the FEC. We're able to figure it out through the FEC, through the redundant packet that's coming in. Does that make sense? So was this helpful?
Yeah.
Got about 15 minutes left or thereabouts. This is what I wanted to get through, but this is what I wanted to go through, all the copper and DSL stuff. As you can see, I utilize these graphs on the DSLs because they show me stuff that I'm not necessarily going to see unless I run a good pair check, or if I've got egress noise or something else. I'm never going to find that in any of the measurements I do unless I'm actually looking at a spectral analyzer to see that stuff. And the graphs have all that built in.
Which test set or test application would you use to test G.sh DSL?
You have to have a G.sh DSL. Nobody has a test set for G.sh DSL. What you're going to have to rely on is the ADTRAN cards. So G.sh DSL is typically symmetrical. It could be symmetrical T1s or symmetrical Ethernet. It's typically symmetrical Ethernet. So what you would do is you would send an Ethernet signal into the G.sh DSL card and maybe run an RFC 2544 or a loop back and get that back on the other side to make sure. But all the G.sh DSLs and all the HDSLs, there are standards to it, but everybody has their own proprietary way of doing it. So nobody makes test sets, test equipment to do that. You have to generate a signal in and read that signal out, or read it to or send it back on a loop back.
Gotcha. Thank you.
Yep. So folks, we've got a few minutes for Q&A. Was this helpful today? Did you pick up anything?